Oh man. All right. So it is time. We are live. Welcome, Jolo. It's always good to see you. Making sure my mic is all close enough and check my levels. I didn't actually take the time to do that before I went live. Probably need to go a little bit hotter on the mic. How's that sound? Good? Good. All right. So where did we leave off? He asked rhetorically. So here we are. This is the current state of the engine. We basically got texture inspecting and editing working. And while we were doing that, we came up with a damn good API for creating custom inspectors. Oh, I almost forgot my Twitch overlay. Let me add that so I can see what people say and my core temperatures. Get my core temperatures going. Do you have any good resources to learn C++? Yeah, I know of a few. Probably the place that I would direct most beginners would be the Cherno's video series, which he's not perfect. He kind of glosses over a few important things, and people argue that he doesn't teach things in the right order. But the Cherno C++, he has a style that I find really good for learning. He's got a C++ playlist, and I'll link it. I'm afraid I don't really have too many suggestions about books because I haven't read too many C++ books. I've read like engine architecture books, and the rest of it I just taught myself from learning from the C++ reference. But let me copy this playlist and send it over to you. Damn, it's a very good one. Yeah. So back to the engine. You're welcome. Back to the engine. So we got the inspector working, got a good API for creating inspectors, so we can even do multi-edits on multiple texture assets. Some of the nice-to-have features that would make this really useful, such as custom thumbnails, we're going to worry about later. What we're going to work on next is materials. Let me open up a scene real quick. So here's a scene with 12 entities, each of them has a sprite on it. This is a placeholder for the renderer 2D, and we're on the road to getting an actual renderer made. And one of the key components that we need to provide is the material system. We had started work on the material system, or started developing it, and then came across some problems that caused us to take a detour and actually go and create texture assets, which are going to be an element of materials. I'm going to turn that music down a little bit. That would be here. We're listening, of course, to the Riot Games sessions. Very good, very generous collection of music that you can use copyright-free. Anyway, so the thing that I'm thinking about right now, the thing that's going to make this a little bit tricky, is how we define the materials. So the problem arises from the way that shaders work. Up until this moment, we've been using a custom preprocessor to handle everything we need in GLSL. However, I've encountered, with the question of materials, I've encountered at least one edge case that's going to make this really difficult. And that edge case has to do with batching textures. So let's explore what that means. It's important that I kind of cover the weaknesses of the current system, because I'm gonna overhaul the system. And there's got to be a good reason for me to do that. So presently, this is a GLSL file. We use the GLSL linter and get the nice types coloring going on, so that way, or syntax highlighting going on, so that we can kind of more easily interpret this as GLSL code. However, we have several extensions The first is these lines, the EP shader line, the vertex line, and the fragment line. So normally in GLSL you compile your shader programs separately, or your shaders separately. So what you think of as a shader, a lot of times people will just say that this is a shader effect, but the shader, what you would call a shader in GLSL is a shader program, and each node of that program is what you call a shader. So they couldn't have made the lexicon like any more confusing because there's like 3 or 4 different ways to refer to the term shader, and they're all correct in different circumstances. And it's more confusing when you bring in discussions of shaders in Vulkan and DirectX and Metal, because they all have their own terminology. But normally in GLSL, what you do is you compile your vertex shader, then your fragment shader, and then you link those together. And there's other kinds of shaders too that you would also link in there. So if you wanted, you could do a geometry shader, and then you have a pipeline going from vertex to geometry to fragment and so on. Now that's that's potentially multiple files for a single program, and you could think of it as a modular system. It's certainly possible to do combinatorial shader programs where you have multiple vertex shaders, multiple geometry shaders, multiple fragment shaders, or whatever, and then you just like mix and match depending on what you need. The trouble with that is that they have to have matching inputs and outputs. You can't just mix and match every shader program to every other shader program inside of a valid program, because you define your outputs from one stage, and then they have to match the inputs to the next stage. So almost always people will come up with something like this, where they will have a way for a single file to contain everything they need to make an entire program. So the way that we do it is that we have an EP shader line up top. This gives Enterprise the name of the shader program, and we use that instead of the path to the file. So that way you can hard code shaders and still bind the shader using its name. Then I'm gonna skip over what's in this section real quick. We have the vertex line, and everything below the vertex line until you get to the fragment line is part of the vertex shader. So it'll basically include, when you go to compile the shader program from this file, it will produce a vertex shader that includes these lines and these lines, the lines preceding the vertex and the fragment shaders. And that will be the vertex program, or the vertex shader. Yeah, the terminology again. These lines of code will form the vertex shader. And then everything after the fragment line plus everything before the vertex line becomes the fragment shader. And that's worked pretty well while I was doing this from code. However, a material system complicates this. So, for example, we do texture batching in the current renderer, and what that means is that instead of simply submitting a draw call for each of these sprites, we have a buffer that we populate with the positions of each vertex and the ID of the sampler to take the texture from, as well, and UVs and stuff too. But the idea is that instead of just having a square, setting a bunch of uniforms and then rendering each one, setting the uniforms again and rendering the next one, we simply calculate all of the positions of all the vertices into world space and populate a vertex buffer on the CPU side. We pass that whole buffer to OpenGL, and then we run it through a shader that takes and interprets the vertex data to identify which sampler slot to take the texture from. And so we have a whole header here, and headers are another extension I've got going batch-textures.glsl. And the point of this is to provide macros by which I can either use a batch renderer or not use a batch renderer. So if you're talking about a rendering an object with complicated enough geometry, like a huge number of vertices in the object, it's not faster to batch that, because you have to you'd be talking about transforming all the vertices in that giant object on the CPU on the CPU side, alongside with a whole bunch of others. So whenever you do batch renderer, generally speaking, you'll also have to support non-batched rendering, where you don't use sampler slots, you just use a regular sampler uniform. So that's the point of these things. btex pass, let me highlight the objects that in question. btex sampler 2D, btex pass, and btex. These little macros are definitions. We put them inside of this header file, and GLSL supports preprocessor definitions similar to the C preprocessor. Actually, it's modeled after the C preprocessor, so almost everything that you can do in there, you can do in here as well. We have btext sampler 2D is a macro that will either do a declaration of an input attribute. So an attribute is the thing that you associate with each vertex rather than a uniform, or it will just declare a sampler 2D, depending on whether or not you're batching. Then btex pass will either take the input vertex attribute and pass it through to the sampler shade, or to the fragment shader, or do nothing, depending on whether or not we have the batch textures. And you can see how this goes. Inside of the fragment shader, we use the btex macro to either sample from the array of samplers, which we had declared inside of the vertex shader, if and when we are doing batch textures, or we are doing nothing. We're just accessing the texture directly. And the whole point of this is that we want it to be optional whether we're batching textures. The place where this gets complicated is when we actually go to declare the textures, or the sampler, I should say. Because if we are not batching, we simply do a uniform sampler 2D. This is where it gets inflexible. Uniform sampler 2D, that's just the texture. If it's not, then if we are doing textures, or texture batching, then we will do an array instead, and then that array is what we access from those macros. And this gets inflexible because when we talk about materials, we're talking about shader programs that may require multiple texture inputs. You know, it's very common to do a albedo texture, and then a normal texture, and then a metallic roughness texture, and things like that. Each one of those would have to have its own sampler 2D array, and it would have to be of a variety of types. And so, like, in order to do like all of this in GLSL preprocessor land, like we'd have to have a significant amount of knowledge about the situation. So for starters, I have the number hard coded 16 here. We would need to know the maximum number of texture units. So that is inside of the fragment shader. You can only have so many textures bound and used at one time. So we would use perhaps the GL max texture units constant, which is provided by GLSL, to determine how many textures we can do at the same time. That's cool, that's fine, but we have to do math on it. So if we have a shader program that has 3 texture inputs, then we would have to have each, I'll just quickly mock this up to demonstrate my point. We'd have to have each one of these each one of these would have to be GL max texture units divided by 3, and this is an integer division, so that would round down to the nearest integer. Because we need to know, first of all, the number of textures is defined by how many lines of these there are. So you would have to like look at the program from the outside to know what number to divide by. And then you'd have to be able to do this at constant time, because you can't declare an array in GLSL with a variable as the array size. That's not how that works. If I'm gonna do a array of samplers, I have to, with a capital H, know how many samplers there are at compile time, which means that the number 3 here, we'd have to provide by like a macro. It'd be like EP num of samplers, something like that. And so prior to compiling the program in question, I would have to, on the enterprise side, provide a special definition to replace this with however many samplers there are inside the program, and then go from there. And then, yeah, and it starts to get messy, because in order for me to even know how many sampler 2Ds there are, or sampler 1D or 3D or something, or CubeMap samplers. I think it's like sampler cube for CubeMaps. Like, in order for me to even know like how many of these there are, I have to introspect the program, which means that I have to have compiled it successfully first. And it's not exactly a catch-22, because there's ways for us to approach this. But it gets really messy. We could, for example, compile a program once, do it as the non-batched version, where we just do regular sampler declarations inside of our program, just one-off textures, not arrays. And then after the program's compiled, we then introspect it and say, okay, we have these numbers and types and names of samplers inside of this shader program. And then we can use that to define EP nums, number of samplers, and then recompile doing arrays of samplers instead of doing one-off samplers. But that means that we have to macro this whole line anyway, which, it's not impossible, but it's tricky. This would be, instead of doing uniform sampler 2D, it would be like a macro like EP texture 2D or something like that, and then wrap it in parentheses like that. And so like we would have to have conditional compilation for this to compile into either just a single sampler, that is a sampler 2D, or compile into an array with a as of yet undefined number of samplers to divide by. It gets messy. And it's, again, I think it's totally possible to do this. Like I can see the through route to making this work. It would be just inside of a regular shader program, you would use a special predefined macro to declare the uniforms inside of, let's say this is the material. We would say inside of the fragment layer, we would just do like EP texture or sampler 2D or something like that, and make this a macro that where we can provide it a name, sampler 2D, and then like example, and then like have like the macro automatically compile without batching. Then we use introspection to compile with batching, and so on. But even this has got edge cases, because what if I want to use a sampler array like for the sake of actually like having a sampler array and not just for batching? Like where does that fit in this equation? So yeah, it's not impossible to work through the scenario, the GLSL style that we've been doing so far, but it's tricky enough that I think we should reconsider the way that we do shaders. So this is going to be a bit of an exploratory stream where we try and figure out the best way to do that. And I've been thinking about this problem for a bit, so I've got some ideas right off the bat, but I haven't really decided exactly how I want to do this. So what I'm thinking at this point is that I probably need to go meta. I probably need to do a file structure that's not simply GLSL code with a few extensions. If you've ever programmed shaders in like Unity, you'll know that when you do shader programming in most other engines, you're not just writing shader code for the most part. You were also interfacing with the engine in a few ways. Unity is the example I'll draw on here because it's so easy to understand. Well, it's relatively easy to understand, but it's also popular and it's held up. Unity uses something called Shader Lab. Shader Lab is a meta language basically for shaders. Instead of just writing GLSL or HLSL or CG shader code, you do this like JSON style thing where you define a pass and you define your inputs and your material properties go into like a properties block and so on. But like this is what these are the sorts of problems that Shader Lab addresses. Because if you define your properties separate from your shader code, even if it's in the same file, then you can simply read what properties there are without having to compile and introspect. You don't have to do a whole bunch of substitutions. You don't have to go in and add macros to your GLSL to make it work. You can just automatically include the correct lines depending on the kind of shader you're building. And then just like from the outside in, you have a file that defines the inputs and outputs of the shader programs. Well, more accurately, you would define inputs and outputs because you have to define what kind of outputs you have for your fragment shader. And then you write the code for each stage independent of those inputs and outputs. And then if you want to do batching, then you simply the engine simply will take care of it. The engine will either declare samplers by themselves as uniforms or declare sampler arrays for the sake of batching. And I think that's a good way to go about it. I kind of thought it was ugly at first, and that's why I think I kind of went all in with doing a GLSL preprocessor up until this point. But I guess this is kind of the value of doing your own engine, is that you kind of learn why things are necessary and the problems that they solve. And so it's not really it's now that I'm kind of in the weeds, so to speak, it's a lot more obvious to me why Shader Lab exists. So we're gonna need to do something similar, I think, and this is where I'm not quite I don't quite have a solution. I'm thinking that I want to do this in YAML, and I'm kind of doing a mock-up real quick to see how that might work. Because in YAML has a couple of big benefits. First, it's easy to parse, it's easy to read, and it's easy to write. That last part is particularly important because whatever format I pick for doing my shader files, it's going to be something that you code. This is like, so independent of the editor, you will be opening up these files in a text editor and writing code in them. And so YAMLs is probably my preferred way to do data storage inside of text files because it's easy to read and write and all of that. However, I'm not so sure about how I feel regarding writing of code. So for example, this is a string block inside of YAML. When you do a key when you do a value that is preceded by a pipe character, you're making a value, I think it's called a scalar block. And in YAML, these values that are simply values are called scalars, even though they could be strings or it could be anything besides the mathematical definition of a scalar. And so this whole thing is a scalar. I can write in, you know, braces and colons and whatever, and it will continue to be a string scalar until I go out one level, and then we're back to YAML. And this kind of looks good. You know, I'm not gonna lie. This is probably the most promising solution I have right now, at least off the top of my head. Because it's well formed, it's easy to read, and it's easy to understand. It plays nice with the YAML parsers that we're already using. However, the thing that I don't like about it, well, there's two things. The first is that the syntax highlighting for GLSL is gone. What if I was to change the language on this? Actually, I wonder what that would look like. Yeah, it's weird. Syntax highlighting still I just changed the syntax highlighting from Markdown language, or so from YAML language to GLSL. But like all of these elements up here, like they don't really work with it because they, like these colons are turning purple and the minus signs are turning purple because it's like they're operators. And while this highlighting seems to be decent, it's awkward. It's not like, it's not really super clear, and it's hard because I want the experience of writing a shader to be nice and elegant. I kind of want the formats to play nice with the linters, and yeah, I don't know. I'm on the fence about that. When it comes to the shader lab itself, their format was basically to, let me find it, basically to use a combination of like JSON blocks and just like straight up like text keys. Here we go. This example code demonstrates syntax from using a material property to set the units value of the shader lab offset command. Okay, so shader, this is the shader name, this is the folder that it goes in, properties. The properties are your inputs. So they have a offset unit scale that you can set inside the material inspector. And then subshaders are what they call the shaders, the equivalent of shaders in GLSL. And then you have passes where you have multiple versions of it. And so like inside of these blocks, you write your code in HLSL. So like, I don't know, we could do something similar to that. If I was to change this to be like JSON style, let me think about that. It would be like, it won't actually be JSON because I wouldn't want to do, commas everywhere, because just making sure that the commas are well formed can be sort of complicated, and it's unnecessary from a developer standpoint. And it would be like just doing a quick mock-up to see what this would be like. So we're not doing commas outside of the braces, but we'll do commas for lists. Yeah, the only problems that I'm seeing is that the curly braces are getting colors that yeah, and Yeah, I don't know. I feel like this doesn't really solve the problem. Right now the GLSL syntax highlighting is still active, but even like doing JSON style, we're not really getting away from like the clash of colors present. It might be the case that I'm gonna change back to YAML syntax highlighting. It might be the case that we just have to put up with not having syntax highlighting in order to make this work. We could then do the YAML style where we have the shader name. We can list the dependencies as a sequence, and then we're not having to parse out the includes from the GLSL code anymore. We'd have the inputs. I guess we should call these properties. That's a more correct parlance. The properties would be things that we set as material uniform buffer properties. And then we'd have like vertex and fragment block scalars, and I guess they wouldn't even have to be like, I wouldn't even have to prescribe them being blocks. I just would probably almost always see it this way with the blocks, so that way it's easy to tell when you're looking at the program whether it's, I'm gonna copy and paste this stuff. Be easy to tell from just like looking at it what's the program and what's not. Yeah, this seems to be okay. This might be the way we have to do it if we're going to be doing because like I wonder if Unity Shader Lab has an extension. Because from from a language perspective, I don't think that there's a way for us to mix these formats. It's either we do pure YAML or we do pure GLSL in order to get our syntax highlighting. And obviously you can't just do programming in YAML. It's not a programming language. Setting aside the fact that I don't want to write a compiler for this. The only other alternative I could think of would be if we somehow got all of this metadata stuff into GLSL without having to work so hard at it. You know what? Let's take a stab at that, actually. So we're going to continue to use the simple material.glsl as an example. I'm going to try a mock-up of this shader that uses like a meta format of some kind to identify all of the inputs and outputs and reduce the heavy use of macros to make everything work. So for starters, having the pound whatever, pound vertex, pound fragment, that seems to be simple enough. It doesn't mess with the syntax highlighter all that much. It's just treated as like a, I don't know, like a variable or something. We'll keep those as they are. We'll do this EP shader line still. However, instead of doing include lines like this, we would do like a block. So this would be like dependencies, like that. And then we just list the files that we want to include. We're still going to do includes. So even though I'm kind of replacing the purpose of the batched textures.glsl header, I still think that game systems like lighting systems, for example, or wind simulations, I think that those will work best if you can just write them inside of write their shader stuff inside of a separate GLSL file, and then be able to just like include that anywhere that you want to utilize that system. So I think that will probably still do includes. And then we would do properties as its own thing. I think that makes sense. I suppose there's not really a reason for us to do the pound, but if we were to do something else, if we were to do I know that Shader Lab actually does something similar to this, where they just instead of doing like JSON style braces or whatever, they'll just like do the word in all caps, and then the preprocessor will just like treat everything after that in a certain mode until it finds like the end. Like I think they have like a begin and end CG, for example, for CG shaders. So it'd be like something like that, where you have like a block and then this whole thing is in one mode and this is in a different mode. The end dependencies is the magic word that takes you out of the dependencies mode. That's not necessarily horrible, but I think it's a little ugly. The advantage of having a symbol like a pound sign at the beginning is that it sort of helps your eye visually delimit what you're looking at. It's kind of like having the hash symbol, the number sign here in front of vertex and fragment. It kind of makes it easy to spot these two sections visually as separate. I don't know, maybe that's just me. Yeah, if we did something like this, we could just have lists, and then I would, instead of doing, instead of having to do macros, we would just be like sampler 2D in-text, something like that. That seems okay, but frankly, it's less nice than just using YAML. And plus, with YAML, we just pass that into Rapid YAML, and Rapid YAML will take care of all the parsing for us. So here we are, 45 minutes in, and we're just still talking about talking. Yeah, so here's what I think I'm going to do. I'm glad I took this time to look through all of these options, because I don't want to be rushing into a bad decision. I think what I'm going to do is I'm going to do YAML. I'm going to go this route. The reason why is because it's well formed. It's easy to load and read. However, as a long-term goal, I think I want to provide syntax highlighting for these files. So that is actually have like an extension for Visual Studio Code that will take and identify when we're inside of a vertex block, and then apply GLSL linting to it, for example. That will be a whole thing of its own. But that would be like one of those nice to have things where it's like when you're working in Unity Shader Lab, like you have that. You're while you're doing code in Unity, and it just occurred to me that I probably should launch these other engines so that they're open while we're working, and I don't have to wait for them to load before I go to check something out in them. But like in Unity, like when you're working in the Shader Lab format, whichever tool you're using, whether it's Rider or Visual Studio, I believe that they have a combination linter for that, where it'll do the HLSL in HLSL syntax highlighting or whatever. Like if we were to look inside of the Unity shader stuff, there's debugger for Unity, Unity tools, Like, what's in Unity tools? Do we have shaders in here? There's got to be something. Shader Lab VS Code. Yeah, this looks like it's third party, but you get the same difference where it actually does like the syntax highlighting and populates code completion for CG and stuff like that. It's yeah, I think that's probably the route that I'm gonna have to go, just for simplicity's sake. And then until that time, when we go to write the GLSL code, we'll have to I'll have to do like an awkward switching between that linter and this one. And then yeah, it's gonna suck for a little bit, but we're making a platform for developing this stuff. We're not using a platform, we're making one. Okay. The only thing that I'm now that I'm thinking through this, the only thing that I'm stuck on is Xcode. It's surely possible for me to make an extension for Visual Studio that could do the syntax highlighting. I've never done it before, but I know that there's support for APIs. I don't think Xcode is extensible in the same way. Custom Xcode. Custom Xcode. I guess it would be a linter. How to create an Xcode linter for Swift. What somebody made in a Medium article. SwiftLint is a great open source tool that makes it easier for you to follow Swift styles and conventions. Okay, so there's something called SwiftLint. Let me take a look at it. SwiftLint, a tool to enforce Swift style and conventions, loosely based on the now archived GitHub Swift style guide. SwiftLint hooks into Clang and SourceKit using the AST representation of your source files for accurate results. Interesting. Integrate SwiftLint into your Xcode project and get warnings displayed in the issue navigator. Okay, so I guess it's possible to do plugins into Xcode that will do this. That's going to be like a stretch goal, though, because eventually, eventually the build system will be such that when you're inside of Enterprise, let me open up projects in these so that I have them. When you're inside of Enterprise and you go to like create a project, like new project, you will be able to choose between VS Code and Xcode, or VS Code and Visual Studio, depending on your platform. And perhaps also between those things and CMake. So if you wanted to have like a CLion or some other CMake powered IDE, you could use that as well. And so to fully add support for those, I would probably want to have extensions for all of my options that provides the correct linting and provides the syntax highlighting for GLSL code inside of the other. And eventually, now that I'm saying this, it's not just going to be GLSL. We will probably be doing HLSL eventually, and then using SPIR-V to cross-compile. Yeah, okay. So I think that like this fits into my long-term plans. It's also simple enough to get started now. Just having to put off that nice-to-have feature for being able to have simultaneously have the YAML formatting and the GLSL syntax highlighting. Okay, but I think that's how we'll get started. So I will close out of this mock-up I've been doing. I will undo all these changes that we've been making in these files. And I guess we'll have to start start coding. Finally. So really quickly confirm everything still compiles fine. Good, I didn't break anything. And we're gonna need to come up with a strategy for how to implement this. Because by definition, what we're doing is going to break the renderer that we already have. Currently the renderer, opening up a scene and displaying it. Currently the renderer that we've got uses the include system and uses the macros to do everything from batching to loading up the enterprise like model view projection matrix and stuff like that. So we'll have to kind of replace all of that infrastructure. I think there's a little point in us working in the editor for today. I think we're probably going to do all of this inside of the test game. So I'll switch over to the test game target. Actually, I'll do it through the launcher, specifically so that way I can enforce DLL boundaries. The launcher, or the game code that we have running right now, is just you can drag on the window to move the camera, or pan the camera around, and then you can use the arrow keys to move around, and then you can press escape to quit. And that's going to be sufficient for our purposes. Inside of the game project then, so we'll go to testgame.cpp. Inside of the game project then, we will, instead of doing renderer 2D init and using renderer 2D at all, actually instead of doing any of this, what we can do is we can do a game scene that will have, let me think about this. We'll do a test state. So currently test state is this thing, where we just have the camera controller and we display the scene. Instead of displaying a scene file, what we'll do is we'll hard code some stuff to display in the scene, and then we will test the shader as we go directly. Okay, so I think that's probably smart. Let's review quickly what we have test state doing. Test state has a whole bunch of extra little things in it that we don't have enabled. Inside of test state, we were doing, we load the input and we do the camera and all that stuff. We also were doing, for a while at least, we were doing text rendering in the scene. We've gotten rid of that now. Yeah. So what we're going to do is going to break what we've got already. So I think I'm just going to take over the test scene section. Inside of test game, I'm going to disable renderer 2D. As a review, when you're making a game in Enterprise, you have game sysinit and game syscleanup. This is where you would initialize things that you want to integrate into your game and into the editor. And if your system is structured well, then you can literally just call init on that system and then it'll init. And so that way we can do things like renderer 2D init and renderer 2D cleanup, or lighting system init, lighting system cleanup, or whatever third-party thing you want to drag in here. You just init and clean up in these calls. So right now there's no game systems. We're not going to do game system. We're just going to do this as a game state. We're also going to, I'm going to comment out editor play init for the moment, just so that there's not a discrepancy between here and there. Actually, I'll do one better. I will replace the code in game init, with the exception of the load scene file call, with a call to editor play init. And basically the idea is that when you go to play the game, it'll run this code to actually set up the game state, and then load the scene file. And then if we do go to switch to working in the editor will play the same game code, but it won't load the scene for you. So that's simple little way to do the same game state when playing in the editor and playing in the actual game. So we'll say game state matches, initial game state matches editor. Cool. All right. I suppose we should call, just for the sake of being complete, we should do the unload call for the scene as well. Or maybe no, I'll just leave that for regular cleanup. So when the scene manager gets destroyed, it will automatically erase everything that's in the scene. Good, okay. We'll still do the subscription to controller wake events. So during the start of play, we will wait for an event to say that a controller's been interacted with. So I'll plug in my Xbox controller so that I can switch to it if I want to. The idea here is that no matter what, this is a single player thing. No matter which controller you're using, it will be the current controller, because we will identify the Awoken controller, we will unpack the controller ID from the event, and then bind that to input stream 1. And we return false because we're not treating this controller wake as handled. We can still receive, later on in the code, we can do subscriptions to controller wake that will supplant this. All right, and then this is the important part. We push the initial test state. So I will comment this out, and I will do a new state that we will use for the sake of testing out the material system. So it'll be very similar, but we'll start with something fresh, so that way we're not. So that way we still have the test state to work from when we are done with all of this. So this will be test materials state. And this state is not going to take any constructor parameters, so the call for pushing the state will just be this. We need to have the class though, so instead of including test state, we'll do test materials state. And then we need to add that file to our source. So we'll do the first one will be test materials state.h, and then we will do test materials state.cpp. We now need to add these to the CMake list. So in here we'll do test materials state.cpp, and you guessed it, test materials state.h. And then that way the build system will recognize them. Okay, configuring, generating, build system, build files have been written, perfect. Cool, so the configuration went fine. We'll do pragma once here, oops. And then we need to do, are we doing I forgot if I'm doing no, we're not. It looks like we're not using a namespace for the game. In a real project, you probably would, but for our purposes, we're not going to bother. We need to have a class that's test materials state. So in here, we're going to do include enterprise scene manager.h. That'll give us the ability to do, oh wait, not scene manager, state manager.h. And this will give us the ability to create states that'll interact with the state manager. So we'll do a class test materials state. It'll extend a public EP scene manager or state manager state, and then we'll base what we do off of that. Probably we'll just need to do init. We'll do init, update, and draw. Probably don't even need to do cleanup. So we'll do void init override and then void update override and void draw override. And do we care about cleanup? I'll add cleanup if we need it. But we have the declarations here. We'll hit save, and then inside of the test material state, we'll include the main header, which is test materials state.h, and then we will do the definitions for these functions. So. Okay, right? Are you good? You're good. All right. All right. So now we've got the core calls for this state, and I'll quickly just confirm everything's working because it's been a while since I've done state code. Ordinarily, this is the sort of stuff that you'd be writing all the time when you're developing a game, but I haven't done this for a very long time. I'll do eptrace. Oh, I need to include enterprise stuff. Let me put that back. So we're doing enterprise state manager. We should be doing include enterprise. I used to have enterprise.h to just include everything that you need, but that's a giant header, and I don't think that's going to be very performant in a lot of cases. So we'll just include what you need. Is the current strategy. So we'll do enterprise core.h. Core.h is a header that includes just a lot of things at once, but I think I'm probably okay with that for the sake of keeping this simple. We'll do include, well, I'll just start there, include core.h. And then we can do eptrace, and I'm just going to quickly confirm that the wiring is all good by doing some console logging like this. Draw. Save that. Good, good. And right, and then in the test game we have the red squiggles have gone away. We've included the test material state.h, and then during the initialization we do a push state. And push state is a fancy templated thing where your template parameter is the class, and then you pass in the constructor arguments if you have constructor arguments for your class. We don't need them in this case because we're using this as a game mode state and not as a like a sub menu or a sub state. So yeah, we'll just construct it without any arguments. But yeah, let's compile that and see if it works. Hopefully we didn't break anything. I don't see why we would, but you know, you check yourself before you wreck yourself. Okay, and linking shared module. Yeah, okay, seems to be working. And if we go to run it, cool, nothing is broken. But if we look at the debug console, we've got draw and update, and on top of all of those draw and updates that we see every single frame, we should have test material state init. So right, so we were attempting to load. You'll also see we've got a couple of errors here that says load entities from YAML sprite is not a valid component type. That's because I still have the code for loading. If we go back to test game, we still have the code for loading the basic scene file in a game. And right now that contains a bunch of entities with sprite components on them. Because we aren't using the renderer right now, we've commented out the renderer init. The engine doesn't know what a sprite component is, so that gives us errors. So I guess for now I'm going to yeah, I'm gonna comment out the include. So just for the sake of making this simple, I'm gonna go ahead and bring the initialization code back into GameInit, like this. Yeah, I think that makes sense. Awesome. So build it now. Or actually, let's comment out all the updates and draws. Just want to confirm that we don't have any. We should have a clean slate on the debug console. Okay, there we go. And take a look at the debug console. Seems to be a-okay. We've got the init, so the wiring is fine, and we don't have any other error messages or anything. Perfect. So that's where we're at. Now we're gonna need to set up a simple state for displaying a few things. So we'll need to have include enterprise graphics.h. Normally when you're writing a renderer, you would include this. We're going to do the rendering directly inside of this section. So we'll do an EP graphics texture handle. I'll say we're going to be using a number of these elements quite a lot. So I'll say using enterprise graphics texture handle. And then I guess shader. Do we have shader handles? I forget offhand whether that's a thing. No, we don't. So cool. So we'll have using texture handle. No, we don't even need to do that, do we? Because we're only going to use that for the declaration of the texture handle. So yeah. So I'll hold off on all that. We're going to need to have a material load call. Yeah, so this is, we're going to do this in the style of test-driven development for a little bit. That is, we're going to write some code that will not compile. And then our purpose will be to write to the code that will make it compile. Not exactly test-driven development because we're not doing the smallest amount of code that will solve the test, but it'll still be fairly simple. So inside of graphics.h, let's go there. Graphics.h does have the materials.h header, which is, we had started on the API before we got sidetracked and started working on the textures. So let's review what we've got, confirm that it still is a good idea. We've got load material, we've got material handles, we've got release material, we've got bind material. I think that makes sense to be able to just do all those things. Excuse me. So for that to work, let's go to the implementation file. Right, we were doing some YAML stuff, and all this code for the YAML parsing, so much code because of the way that that's YAML CPP requires you to do try-catch blocks all over the place, which is part of the reason why we are switching to RapidYAML. So we'll include ryaml.hpp for that, except for angle braces because it's a external library. Good. All right, materials. So we have string to text filter, string to bitmap mode, and so on. That code's not necessary anymore. Previously, we were starting to just parse out the information associated with the texture, but now we don't do that because we just parse out the string path to the texture asset, and the texture asset contains that information. So load material. I'm going to go ahead and uncomment out all of this. Oops, I selected too much, I think. There we go. And we're going to need to make a few changes. So for starters, load text file, parse YAML. We had a material format that we were working on. We're going to need to take a look at that. So we have simple material.epmat. This is where we got started before. I'm going to do configure an association with .epmat. We'll associate this with YAML. Go ahead and do that right away because I'm like 100% sure that this will be YAML. cool. We got the name of the material, the path to the shader that you're going to use, and then we got the inputs. That's right. I'm piecing this together now. So each input, right, and this is where we got sidetracked. These elements here are now no longer part of the no longer part of the material file. That's stuff we're going to be doing inside of the texture asset file instead. So I guess that would be. I guess what we would do is we would do paths to texture types, so or texture assets. So we have the name. That's going to be a key value pair for the shader as well, because it'll just be saying that this is the path to the shader, this is the name of the material. However, in textures, these are going to be sequences basically. Well, not exactly sequences. Because after we've loaded the shader, after we've compiled the shader, we will know inside of the metadata we get from the shader file, we will know what its properties are. So what we can do is we can do a make the textures value itself a map. The map will be the name of the sampler property. I'm going to say sampler property name, just to make this a little bit clearer to me reading it. This will be the name of the input listed inside of the shader. And as part of this test, we're actually going to give proper names to these things, but I'll skip over that for the moment. And then the value for that key will simply be the path to that asset. So it'll be C textures example text.eptext. Okay, so that's pretty simplified. Properties are going to be a little bit different from texture inputs. I mean, you could argue that textures are properties. Well, you know what? The reason why I was keeping those categorically separated probably doesn't apply anymore. Because when I was originally going through this, like a week or two ago on stream, we were still in the plan, in the mindset that everything would be handled in GLSL. So because of that, textures were kind of necessarily separated from the rest of the properties, because these properties would be defined inside of in the implementation in GLSL. These would be handled inside of the materials uniform buffer. So a special uniform buffer dedicated to properties. Whereas these samplers can't be loaded that way. And so what we would do is we would make those sampler uniforms or sampler uniform arrays in the case of batching. However, now that we've got, let me take a look at the, I'm going to open up the textures. Wait, no, that's not right. Let's go back to the mockup we had for, oh, I got rid of the mockup. That's right. God damn it. So in the mockup we had going for the GLSL file, where we do the EP shader file. So that has the meta information in YAML, and then the shader stages in as key value, or as block scalar values. In there, we had a properties block where we defined all of the inputs. I could simply put textures in there, and then have the implementation, so the OpenGL layer of the game engine automatically handle splitting those up into either being in a material, either being a part of the material uniform buffer, or being a texture on its own. I think I like that a fair amount. Yeah, I think it works too. So when we do the types like this, the values will have to be, the type of the value will have to be contingent on the type of the property. So we would just have another, type, which would be sampler 2D or something like that. And then the value would be the path to the texture. Okay, I think I kind of like that. I think I like that idea. Yeah, and that'll simplify things a fair amount. Okay, so for the sake of our test, though, we're not going crazy with material properties. At some point, we'll have to define what all of the types that we support will be. But for now, I'm just going to do a simple material. We'll use C shaders. I'll do C materials, and we'll do the material tests inside of here. C materials, simple shader.glsl. Okay. And then in the properties, we will do a sampler 2D. That's going to be main text is going to be the key. And then it'll be a type sampler 2D. The value will be the path to the texture. And then we will have to do, in order for proof of concept to work, I would need to do at least one regular uniform property. However, I'm going to hold off on that until we have got this part working, because in order to get the other kinds of properties working, we would need to get the implementation for the material uniform buffer going, and that's a big old task of its own. So we'll get this working, get it tested, make sure that it's working, and then we will add the properties buffer later. Okay, I think we're making progress, even though nothing is compiling yet. Perfect. So name, shader, properties, and then, yeah, am I forgetting anything? Let's take a quick gander at a material inside of here. So here's a material that wait, is this the material? No, this is a model. Where did I put the? Oh, I put it in the project. In this Unity scene a while ago, I was kind of playing around with assets I found online, and I constructed materials from a bunch of textures I found online. So I got this ground that's basically these textures are just the like matching normal maps and albedo maps and whatever, and I associated their stuff with the standard shader. But yeah, we've got texture inputs, we've got value inputs. This other stuff that they have has to do with Unity's prescription of their rendering pipeline, which I'm not going to do. Like rendering mode being opaque and whatever, that's a... Oh, here's an interesting thought. I wonder if it might be important to do a custom inspector for materials, like a material being able to define its own panel for setting things, or material shader So like you have like a shader that has a bunch of inputs, and then you can like have like custom widgets in here that will. I'll put that on the back burner. That seems less important at the moment than the general purpose inspector for them. Okay, yeah. So this is as simple as it gets. I will save this somewhere. Right now it's in content materials. Yeah, that's good. We'll need a simple shader.glsl. So we'll save in content materials, simple shader.glsl. I have to actually do GLSL in here. Where are you, GLSL? There you are. And that's where that goes. Good, so this will feed into that. Oh, right, but we're not doing simple GLSL anymore. So we're doing EP shader to indicate that this is a meta shader file, which means I have to rename the extension to be EP shader. So we have an EP shader file now. Cool. And then I'll need a texture inside of, I'll do this in C materials example text.eptext, or I'll do simple text to keep up with the naming scheme. So inside of simple text, then we'll need to add an image and an asset for it. So let's do a new file. This will be this will be simple text.eptext. And then inside of it, I believe we'll open up another texture and copy its elements in. Yeah, like this. So 2D, right now we only support 2D textures. And then we'll need to provide a texture for use. I'm just gonna borrow the same texture one as we've been using so far, which is I think it's Madeline Sprite from Celeste. We'll use nearest to none. That stuff is unimportant for this, because this is a tried and true format at this point. Good. So we've got a texture, simple text that will be loaded, and then yeah. So now everything comes down to these two things interacting well. So this is .ep shader. I'm going to change its format again to YAML. And then we will do a quick mock-up we'll do a quick implementation of the thing. I'll do name as well. This will be simple shader. We need to remember all the things we need. We'll have dependencies. This is where we do the include lines for GLSL files. I'll do. Oh, how do we want to do dependencies? I haven't decided on that yet. Because up until this point, we've been doing just GLSL stuff. This was an example of. This is actually the example of a include file for GLSL, because it's like this is all the stuff that every enterprise shader needs. So it's like you define it here, and then you include the file using the include enterprise.glsl line. If we're getting rid of the old style, where we were doing include on the, like, as if it's a C style directive inside of the GLSL code, and we're replacing GLSL files with EP shader files, how then do we handle headers like this? That's a fair question. Because on the one hand, we could just leave it as a GLSL file, and then when we go to include it, it will do exactly what it did before and just like paste this at the start of the program. That would be one way to do it. and probably the fastest way because we already have support for doing that because we've been doing it all along. However, we may want to wrap this in, wrap this code up inside of a EP shader format as well. Okay. It's tough to see the immediate benefits of doing this, but one would be that its properties would become available inside of its children. So we could do, for example, if we had a system, say, a game system that extended the renderer. So like a custom lighting system that we would do in addition to the renderer. We would want to have a include file that would provide that implementation to your material shaders. So what you could do is add its include as a dependency, similar to how we were doing it before, where we said include this GLSL file. And then it would be able to declare things that needed to be included in your shader to make it compatible with that system. Let's make a list of the things that a include needs to provide, because it's a little hard to fit all of the thinking in my head about this. So so purposes of a shader dependency. Systems can provide their own implementation for features to be used by developer specific, to be used by material shaders, I should say. So this would be this would mean that, like, if you have like a wind system, you write up the vertex shader wind system stuff, or if you do fragment shader style effects on your wind system for some reason, you write all of that stuff inside of your wind system shader file, and then you add that as a dependency to all the materials that want to interact with the wind system, and then you can simply update that wind system shader file to affect all of the materials that use it. So that allows you to just like make changes to your wind system and then not have to think too hard about which materials use which shaders that depend on the wind system. It just works, is the idea. So what sorts of things would they provide? They might provide their own uniform buffers to be populated by the system directly. So for example, with a wind system, you would have like maybe global properties that you would need to set every frame. Like if you were doing, well, for starters, if you were just doing like a direction and a strength, then you would have like a uniform buffer that would contain a vec4, which would contain for the first three elements of the vector. It would be the x, y, and z for the direction, and then the fourth would be like a strength value, and then that would be updated by the wind system, and all of the materials that use it would automatically have access to that uniform buffer, so they can all use the same data at the same time. Okay, and then it would provide such a header would also provide helper functions for its use. Helper functions? Maybe. So in the case of a wind system, you would need to be able to modify the vertices. Sorry, not vertexes, vertices, consistently across material shaders. So you'll also need to know inside of the material shader like how the pipeline fits together, because if you're using multiple systems that affect your vertices, then you'll want to decide on the materials side which order that occurs in. So yeah, helper functions for things like implementing data from uniform buffers. And now that I'm thinking about it, the dependencies will also need the ability to do sampler uniforms. So for example, I'm going to keep writing this wind system thought experiment out because it's just so easy to milk. Thinking about the wind systems, a very simple wind system, like the one I've got going on in Unity here. Very simple wind system would be like a direction and strength, and that applies to the whole scene the same way. And then you can change the strength, and it affects all of the things the same way. However, an advanced wind system would need to do like a localized wind response. Probably the gold standard for that, in my opinion, would be how God of War 2018 did it. In God of War 2018, they have a 3D texture that spans the entire scene, and each voxel of that 3D texture is a vector indicating the wind strength at that position, and that gets updated every frame. The materials that interact with the wind system, they sample the 3D texture at the correct location to identify how strong the wind is near those vertices, and then it does the deformations based off of that. In order for that sort of a system to be implemented, you need to be able to be implemented in Enterprise, I should say. You would want to have a wind system shader dependency. Maybe I should start calling these modules instead of headers. I think that this is starting to become more of a module thing rather than a straight copy and paste thing. It would need to have sampler uniforms that are not material inputs. So by this I mean that instead of simply adding the sampler uniform as a property that's visible inside of the material inspector, it would be a uniform that's visible to OpenGL, but not to you in the material inspector. It would be something that only the wind system would update. It would bind every time you go to draw. Oh, this is where it might get a little complicated. Every time you go to draw, you would need to make sure that that 3D texture is bound to that sampler slot. Okay, that's another wrinkle. Because in the case of such a thing, such like a sampler 2D being used for a game system effect, you could simply declare it the normal way as a uniform inside of the GLSL code, and so that way it's not visible inside of the material properties list, and it won't be visible in the inspector. But then when you go to bind the material, how do you make sure that the correct thing is bound? Because when you go to bind the material, it basically will just take and set all the properties from what you have inside of this file. You bind simple material, it will bind this shader. It will bind this texture to a slot, and the GLSL meta programming stuff will make sure that this texture will be assigned to the sampler 2D that's named main text in the GLSL. But then how would the material system know to contact the wind system and bind to that sampler slot? Oh man, that gets complicated. Not really sure what to make of that. Oh, thanks for the follow, Scary. Scary Hetman. You are breathtaking. I forgot that I put that in my little bot notes. Yeah, man. Every time I think we're ready to go, I think that there's a I come across another problem that I need to worry about. So the material system could, for example, handle like callbacks or something. Like if we had a wind system that managed a 3D texture for shaders that had its dependency, what it could do is during initialization, it could register with the graphics system to say, hey, if you have a material that needs to bind a sampler 2D with this name, ask me to do it, or something like that. We could also do a texture API where we either generate or load a texture, in this case a 3D texture, and then say have a call to graphics. I'll just quickly do some mock-up code to see if this API would make sense. It would be something along the lines of like EP graphics associate texture to sampler, and then it would take the texture handle. So in this case, text would be like the 3D texture that holds all the wind data, and then the name of the sampler that it needs to be associated with. And so something like this call would happen at the start of the wind system during initialization. During initialization, it'll generate the 3D texture that's necessary. It'll associate it to a sampler. And then any material that contains that sampler, the material system would know to bind this texture handle to that sampler. I like that. I like that quite a lot. That's okay, I think that kind of answers that question, because the API wouldn't be so hard to design. It would be very simple to use as well, and it would be invisible to you when you're doing the material programming yourself. So you make a wind system. The person who's making the wind system, all they need to do is make sure that they have the texture that they need their wind system powered materials to use. They would then call associate texture to sampler and associate it with a sampler name. And then when a person is doing when a person is utilizing the wind system's module inside of their shader code, they would be able to start using those values as soon as they import the module for the wind system, and then simply by binding that material, by binding the material that uses the wind system, it will automatically it'll automatically bind the texture that the Wind system provided to that sampler. I think that's good. I think that's actually quite elegant. So these will be bound automatically by a registered texture handle. Or I should say, by a texture handle registered by the system. All right, cool. Nice, nice, nice. All right. I wonder if there's a need for sampler uniforms. A need for sampler uniforms that are material inputs. So this would mean that if you were wanting to make a PBR-based material, for example, you could have a PBR module that you could bring into your shader. The PBR module itself will add the inputs for textures that you need for that model. I don't like that very much because you kind of want to have control over that. You don't necessarily want there to be a one-to-one correspondence with materials. Let me open up. I'm going to open up a material editor inside of Unreal and kind of use that as a point of reference. So I'll open up. I love this scene because it's got a whole bunch of simple materials, and you can kind of just see the power of their material system in Unreal, one of their biggest perks. And I particularly love this material because it's a parallax material, and it's so hard to tell, like even when you know what to look for, it's so hard to tell that these are cobblestones are not actually physically modeled. Like you're looking like straight down or from an angle, like as all the gaps between the stones, they all seem so perfect, but it's actually just a material trick. Let's open up its material. Rendering, there it is. So this is the material editor in Unreal. It looks really, really complicated for this particular material. It's not super complicated. This is just the nature of parallax. In parallax, you'll do sampling of one or more textures from a variety of perspectives to simulate what it looks like when you're going over when your perspective changes. You can kind of think of it like in like the old NES game days where you had parallax backgrounds, but the difference is that each layer of the background is a layer of the material. So you've got the foreground elements will move faster than the background elements, which is how, as I rotate around this ball, the outer layer seems to move quicker than the inner layer, giving you the illusion that there's actually a crack in there. So these are actually all just repeats of the same thing, but with different offsets. But just considering this as like an example, its materials, if we go to parameters, we've got a brick texture, cutout gradient, diffuse texture, normal texture, and these all feed into, I think, a PBR, in here. So this would be the equivalent of a PBR module in Enterprise, where we have the base color, the specular, the roughness, and the metallic is probably in here. Oh, I don't see. Well, metallic roughness is how this is related to metallicness. Oh, there's metallic. Okay, so you get metallic and then metallic roughness and so on. But yeah, if this was to define the inputs of the material, then you would have very little control over what goes into it. So I guess yeah, that doesn't belong on our list. We don't need sampler uniforms that. We don't need the ability for a module to automatically implement a material input, at least not for samplers. What about other kinds of inputs, though? Let me think about this. So additional material properties, textures were just one example of a material property. You can also do like colors and things like that. I guess again, the answer would be no. In no circumstance should a shader module prescribe what the input of a material should be. That should be something that's entirely decided by the material shader itself. Okay. So I'm going to make that note in here. So systems can provide their own implementation for features to be used by material shaders. We got uniform buffers, which is going to be its way of passing non-sampler data. And then we got sampler uniforms, but they are not material inputs. They are just associated with a texture that the system populates and updates. We have helper functions for actually implementing features. And then modules will... I'll start using this terminology. I like the term module for this. I think it's more accurate. Modules will never prescribe material parameters or material properties. Yeah, so that's a total list of all the things that might be relevant. However, getting this through, I wonder if there's a let's think about this. Is there a scenario in which a shader module should prescribe or affect the output of the fragment shader? So this would mean that your material, you write the material one way, and then the module that you've included will add an additional parameter to the output. So that way, for example, if you wanted to have additional data besides the color information in the output of your shader, but have that additional data be defined by the module that you plugged in. That's an interesting thought. So such a scenario, let me write down the question that I'm trying to answer real quick so I can quickly reference it. We would say a system can provide add outputs to the fragment shader. So these things would be basically passed through. Meaning that by adding the module, not only does the module add the additional output to the shader program, but it also prescribes what that output would be. And so that would mean that as the material developer, as you're making a material shader, you don't have to think about what it wants to pass through. The system just does it. So what would we maybe want for that? One way to utilize this might be to do something along the lines of a G buffer or deferred rendering. This gets a little bit tricky because the concept of a deferred renderer is that you do all of your expensive material and lighting calculations, and especially the lighting calculations, after you've rendered to a frame buffer. And then that way you're doing all the lighting per pixel instead of per object, or per vertex. And that can reduce a lot of overdraw problems if you have expensive lighting and there's overdraw factors that makes that expensive. It also makes it so you can do a huge amount more lights or things like that, because you're limited by the number of pixels usually, and not by the number of lights. But a deferred renderer probably wouldn't. No, you know what? That totally counts. Hang on a moment. Let me add a new category. This stuff here that we're talking about was the idea that a module would be defined by a game system or a physics system or something like that that might affect your rendering. In this case, there's also the possibility that a renderer can provide a module for interacting with it. And a key example of this would be deferred rendering. So in deferred rendering, you render out to a G buffer, which contains, for every pixel, it contains a value that's used inside of the lighting calculations, like your normal and your material roughness and things like that. Basically, anything that you would calculate lighting and colors from would go into your G buffer. So if you're using a deferred renderer and you're doing a material for that, then it would define the output of the shader. Because the output there's a lot of thinking to do. This will all be well worth it in the end, I'm sure. The output of a shader, I guess now we're getting a little bit more meta. Previously, the output of a shader program was up to the shader program directly. And then if it didn't happen to align with the currently bound frame buffer, I think it would just kind of gloss over the problem. Let me take a look at how I did frame buffers, because I don't remember quite offhand how we did the binding call on frame buffers. So we have a frame buffer stack, that's right. So we push and pop frame buffers. When we go to push, we call we assert that we have the frame buffer. We call GL bind frame buffer on it. And that's it. We don't do any checking to see that all the inputs of the shader program match the outputs or whatever. We just bind it and then presume that it matches. So in a deferred renderer, we would say the frame buffer is, let's say the G buffer. That's normally what this is called, even though I don't know what G stands for. The G buffer would be defined by the renderer itself and pushed before rendering. And I don't need a comma there. So this would implicitly define the output of the vertex shader, or fragment shader. Okay. So in some sense, the output of a shader program is outside of the shader program's control. If we'd be flipping this paradigm on its head a bit. So I guess it would make sense that if you're working with a deferred renderer, you want your material to be compatible with it, you would include the module, the shader module for that renderer. It would define the outputs of your shader, or at least it would add outputs to your shader necessary for the frame buffer to work correctly. And then it's a little hard to keep this straight in my head. I guess the question is there any situation where you would want inside of the material shader itself to add outputs? And I'm thinking no. I'm thinking that's probably not a thing that you'll want to deal with. So I guess what we'll say is the renderer can provide or can add outputs to the fragment shader stage. This is necessary to ensure, necessary to provide material shader, necessary to make materials compatible with renderer. This also means we'll need to have helper functions for outputs. So if you're making a general purpose material, for it to be compatible with each different system, that system would need to provide a helper function inside of the shader code for assigning your outputs. Let's quickly load up simple material.glsl. So this is the one that we've been using inside of the renderer 2D this whole time. Basically, the output appears like this. It's an out variable that you assign to. So when you go to set the output color for final color, you would have to have a function that, or to be more correct, you'd have to have a macro that would either assign that value or not, depending on whether or not you're supporting that renderer. So instead of doing final color equals whatever, it would be something along the lines of set final color, and you pass the value into a macro-like function, or function-like macro. And then if the material is being used with the system that supports that output, it would have that code as part of the variant. Otherwise, it would be omitted. Okay. So I think that's starting to come together. So thinking about helper functions macros designed in such a way that the material can be conditionally, that material can support other renderers. Okay, and then optionally setting the output variables in specific shader variants. Okay. All right. However, we'll also need to have pass-through. Or I should say, the material doesn't set these, the renderer does it directly. Okay. Okay, so pass-through outputs. And I just thought of a perfect example. One that we'll probably be using ourselves very soon. In some games, it would make sense to utilize the fragment shader's output as gameplay information. And I'm particularly thinking about mouse picking. We're probably going to be using shader-based mouse picking inside of the editor, because it solves a lot of problems that regarding like raycasting in such a way that it's easy to generalize. So when you go to do mouse picking, there's two main ways to do mouse picking. The first is that you do a raycast. So when you go to click, the engine will cast a ray from the cursor position into world space, and then see whether that ray hits some geometry in the scene. However, that depends on having geometry to collide with. I think, I'm not 100% sure, but I think in the Unity editor in particular, I think that it usually will select using the pixel color. So if I go to click really close to the red cube but not quite on it, it'll actually go pass through. Or maybe not. I think yeah, just now I clicked over empty space nearby the capsule and it still selected it. So it probably uses some kind of combination. The capsule here has a collider on it, but these meshes don't, I don't think. If I was to quickly play this game and walk around, yeah, but you know, I think I just haven't enabled collisions. But these rocks were brought in from online, so I don't think I added colliders on them. No, so these things don't have collision models. So Unity still has to know whether I'm clicking on them. And I think the way that it does that is by using per pixel data. So the way that this would work is that when you go to render, the engine will surreptitiously add an additional output parameter to the fragment shader. And the vertex inputs will have an additional attribute as well. That is just the ID of the entity. So this is stuff that you would want to have invisible under the hood. You wouldn't want to be thinking about this as a material programmer or as a game developer. But what would happen is that the vertex buffer that's provided to the shader, the material shader, it would have an additional parameter added to it that just passes in and associates the vertex with an entity ID. And then that passes through all the shader stages down to the fragment shader. And at the very last stage, the frame buffer that you're rendering into will accept the entity ID in it. And then when you want to do mouse picking, you basically just take, and instead of casting array, you simply figure out which pixel of the frame buffer your mouse is over. You sample that pixel inside of the frame buffer, and then you access the entity ID data from that pixel in the frame buffer. And then bam, you know what you've clicked on. And the advantage there is that it'll have 100% agreement between what you see and what you select. So, for example, in the case of like these leaves here. Okay, and this is actually confirmation about what I was thinking. What I was thinking that Unity does. If I click between the leaves, the selection does not occur on the tree. It only does when I click on a leaf which is visually available. And that works because for all of these pixels around, I think what's happening is that we are discarding those fragments. And if we're not discarding them, then we're at least having a zero visibility. So we can probably do some logic that will make it so that logic in the shader to make it so that only the visible fragment will win. But like I happen to know that like these are all squares, technically speaking. If I was to go into the material for the leaves and change the alpha cutoff from this value, which I'm going to copy, down to 0, you can see that there's actually an entity thing there. Each of these leaves are just billboards, and we are using the alpha cutoff to make it look like they are transparent. And so now when I go to click between the leaves, it does in fact select. Say Unity must be doing something like this as well, where it will populate the frame buffer with the entity ID information, and then when I click on a pixel, it will use whether rendered to that pixel to tell me whether I've selected the tree. So yeah, pass through. This means surreptitiously. You know, I don't think I know how to spell surreptitiously. Is that how you spell? I don't think I've ever spelled it before. Surreptitiously, that's right. Add a vertex attribute and fragment shader output to pass information to the frame buffer. Actually, that whole adding a vertex attribute part is not necessary for this, because you could imagine that some shader process would come up with a value that needs to be passed out. But basically, you would be talking about the renderer adding a output that didn't exist before, and that the material shader programmer doesn't need to think about. So this would be similar to the way that we're talking about adding texture inputs that are not visible to the material inspector. Okay. And then I guess that brings up the other possibility that would be adding vertex attribute inputs. However, vertex attributes are by definition not part of material properties anyway. they are part of they're part of the renderer's input data for excuse me, for materials. So basically rendering gameplay tasks with macros with optional macros for handling. Okay. All right, so I think this is a pretty solid list of things. We would be using the modules, shader modules specifically for systems and renderers. Those are the main things. And you can argue that a renderer is the same thing as a system, but I'm gonna treat them as separate because the idea is that a renderer is the thing that actually does the draw call to actually bind the material and do the calling, whereas a system is something that would go on top of that. So for example, a renderer may be totally unaware of your game's wind system, but it'll still support it because the system that manages the wind adds the things that it needs to the material itself. Yeah, okay. I think we're somewhere. So this took a couple of hours just to figure out most of what we're doing. We're still going to have more questions as we go, but I think I've got an idea of what a dependency does. I really need to get something to drink, but before I do that, there's one last question. Now that we have an idea of what goes into a shader module, the last question is, how do we implement a module? Up until this point, we've been doing just a GLSL header, which would be literally just copied and pasted into the shader code before. I don't think that's sufficient anymore. I think we'll need to have something in the form of what we have for the new shader file format, where it's YAML and we got parameters that go in. So we should probably make a list of inputs for. Let me think about this. Yeah, inputs for outputs of a shader module. And I'm saying outputs here because I'm talking about what the material shader will bring to the, hang on a second, what the module will bring to the material shader. Does that make sense? No, that's what this list is. Yeah, this is going to be inputs. Inputs of a shader module. So these are the things that you plug into a shader module file to be used by your renderer or your game system, I guess. So what would we need to provide? Let's go through this list again. So uniform buffer definitions need to be provided. So these are not populated by the system directly. So I guess the short of it is that we'll need to have code to include for each shader program. So this would mean declarations to prepend to each shader stage. We have something similar to that in here already. If we go to the batched textures header, which we've been using, we do it using GLSL's preprocessor, but after this pragma option, which tells Enterprise which definitions to provide when compiling, we have an if-def. Whether or not we're using batch textures, we do this or that. And then we have an if-def EP vertex and EP fragment. And this is to conditionally include this code in the vertex shader and to conditionally include this in the fragment shader. That doesn't need to be if-def if we have our own format. what we could do is we could simply make a section for each shader stage for source code. Yeah, okay. So I think that's a good thing to add. And that's where we would do our uniform buffer definitions for things that are used inside of the module and not used by the material, so not exposed into the material system. Sampler uniforms that are not material inputs. Yep, that's where that would go to. So this would just be, these two things would just go into the source block for that shader stage. That makes sense. Helper functions and macros for implementing features. Yeah, same thing. That's just going to be GLSL code. Modules will never prescribe material properties. Yeah, that's fine. And then adding outputs to the fragment shader. That would be something that you could either do from systems or renderers. So I guess we would need to prescribe output fragment shader output. So when you include the module, it will automatically add output stages to each. You know what? We have to go more general than that. So add input and output stages to input and output, inputs and outputs to each shader stage. So the module can define what goes in and out of the vertex shader or the fragment shader. But you know what? That still could roll into, let me think about this. That could still roll into the source block. So if we have a source block for each shader stage. And let me mock this up real quick, just to make sure that I'm on the right on the right track. This will be like a module, shader module. We would give it a name. In this case, I'll just give it Enterprise to simulate doing this stuff. We would have a fragment section, and it would simply just be the fragment source code. GLSL goes here. And then we would do the same thing for the vertex using YAML block to do that. Okay, I think that's making sense. And then inside of each of these, we could do input declarations, so like in int or unsigned. Int, and this would be like your entity ID. So this would be like simulating a pass-through. We would have an out that would be unsigned int. Oh, okay. So, you know what? We would have to split this up a little bit. Because if we're going to be assembling a shader program from multiple source files, I would need to have some code inserted into the main function and some code inserted above it. So the declarations, like this, it'd be out, flat, unsigned int, out, entity ID. These would be placed at the top of your shader program. It would be like something that you would put like here above your main function. And then code that needs to execute within the function itself needs to have its own block. So it would be like vertex code, like that. And then this would go inside, goes inside of main function. And it would assemble so Enterprise would assemble from each of the vertex codes in the modules and all of the vertex code inside of the regular shader file, what goes into the main function. Okay, this means though that getting rid of main functions, and I wonder if that's a good idea. I guess that would make sense. So changing the mode to GLSL real quick. So source code to, okay, I think I'm piecing this together now. So so in a shader module contents, we will have code to prepend to each shader stage outside of main function, and then code to prepend to each shader's main function. And because modules will never prescribe material properties, we don't have a place to do like this. We don't have to do properties and do a declaration. It would just be like a code block like this that we would declare. It would be the place that you put your declarations, and then inside of here it would be like for continuing the example of passing through the entity ID, it would be out entity ID equals entity ID, right? And then this would go into the main function and execute before the code of the main function in the regular shader. So the thing that I'm getting uncomfortable about now is the idea of separating the main function code from an actual function body, which might be a little bit awkward, but I guess it would be kind of like this. Man, we're getting really inventive. Because what we're typing is GLSL code, but it doesn't look at all like a full shader anymore. It looks like little code snippets of shader code. So I'm just going to continue with this example. So this is a fragment shader algorithm that takes and does some texel math to do anti-aliased lines when you're magnifying pixel art, which is nice if you're doing a pixel art game that has a lot of modern zooming and panning effects. It'll get rid of those jaggies that would appear between the texels if they fill up more than one pixel on your screen. I guess this could work. You know, now that I'm kind of looking at it, the idea is that this code would go inside of this code would go inside of each function. I would say, how about this? Vertex main, fragment main. And so this would be the code that executes inside of Vertex main. And this is code that executes inside of Fragment main. By this I mean the actual main function that executes your code inside of that shader. Then the main function would be assembled from this and this. The stuff that you put inside of the... Okay. I'm liking this. I think this is going to be very flexible. And despite how complicated it looks, it's actually probably going to be way easier to implement than what I had been doing before, which was a full-on goddamn GLSL preprocessor, which meant having to deal with a whole bunch of edge cases, just to break down the language lexicographically. Okay, all right. I think this is going well. Okay, and then yeah, Vertex declaration maybe. I don't know. I might come up with a better name than Vertex Decl, but yeah. So this would be all code that you put in preceding this, and then the way that the modules are assembled, it would be like you would start with the first dependency. Hang on a moment. So in this case, it'd be like enterprise or like C shader modules enterprise.ep shader. It would take and this being the actual shader, it would take and assemble the Vertex shader code from first taking the first dependencies of Vertex declaration section, then taking the Vertex declaration section of this actual material shader, and then declaring the main function, inserting this code from the Vertex main, and then inserting this code from the Vertex main of the actual shader. So it would be like stitching together from all the dependencies what goes into the main function, and stitching together from all the dependencies what goes into the I don't know, I guess the non-main section, because that can include other functions besides main. It would be like the thing that you declare all of your functions and inputs and outputs in. Okay, I think I'm digging this system. As a plus, it's not super distracting to use GLSL syntax highlighting here, because we're not doing a distracting amount of function declarations inside of here. There's no braces. It just goes fragment main, and then we just go straight into the code. Though that wouldn't remain true, would it, for helper functions? So if I was to do a helper function inside of the section above, it'd be like Vertex Decl. That would kind of look like this. Vec4 and it would like return 1 0 0 1, like that. But you know, that's still not very awkward. That's still not bad looking. Especially if I break it up like this. Okay. You know, this is stitching together very well. Like, I think this would be a good system by which I could assemble a bunch of shaders with a bunch of different purposes, but it is quite awkward to read. I'm gonna quickly take a look at a. I want to see if I can grab a shaders a Shader Lab shader that I can compare against. Because to be honest, the bar for me for usability, like the bar that I have to clear, is making it at least as intuitive as the Unity syntax, and it's not super intuitive offhand, so I'm gonna make sure that it's looking fine. So this is the standard shader apparently, built from Shader Lab. So we've got the shader block, properties block, subshader blocks, where we do all of the subshaders. We do CG program, and then we do all the code between CG program and NCG. So this section here is all CG language, or is it HLSL? I don't know. I haven't used either language, but this is shader code here, and I guess it's pretty clear because of the tab ends, and it's also probably more clear than I'm looking at it. Yeah, you know, it's actually not necessarily more clear than what I've got here. The one thing that I dislike is that the contents of the main function are not in braces. Let me try putting braces around this. I'm wondering if this is a sign that I should use something that's not YAML. For this. And if we're not using a YAML, then I would probably go back to doing 4 spaces for the tab layer. Because in YAML, it's like the tab indents are literally how you define your data structures. So for those, for that purpose, we usually went to 2, but it makes it a little harder to identify your code. Yeah, to be honest, I like this a lot better. This is already a lot more readable. Maybe it's just the tabbing though. Maybe that's the problem. Maybe if I was to do get rid of the braces and just make sure that the tabs are 4 characters wide. Maybe that would be enough. Okay. You know what? This is actually probably looking a lot better than I would have. This whole thing with doing names and braces, and then regular tabs. This actually might be enough for me to do my own parser for. This might be simple enough for me to do a quick parser for, but it also might be stylistically better than what we had before. So I've got a lot to think about. I think we're very nearly done with the new shader design. In deciding how dependencies and properties work, let's not forget to add a properties block. And then this would be where we do how are properties done in here? They get the name, and then in parentheses they do the friendly name and the type, and then they give a default value. I suppose if I'm not doing YAML, I could do whatever format I want. If I was to keep with YAML, it would look something like this. It would be a sequence of maps where it'd be like type is 2D or sampler 2D, and then name would be in text or something like that. This would be like type is vec4, name is base color. This is what it would look like in YAML. Huh. Oh, that's interesting. That's handy. It looks like when I go to tab in, hang on a minute. Oh, never mind. The document, the editor changed space indentation to 4. Which I could probably do for YAML as well, but I don't know, like for the metadata, like name, dependencies, properties, the YAML format seems better for me. But when it comes to actually like writing blocks of code, I think I'm just getting stuck on the way that the code formatting looks. It feels like it should be. Let me go back to. No, I'll keep up with 4 because 4 would be how we tab the rest of it. Oh, you know what? Maybe we should be doing in tabs of 4 spaces for shader files anyway. All right, I'm gonna do a quick little bit of homework on our RapidYAML. I don't believe it cares about how deep the indents are. Like how many spaces there are. I'm going to take a look at the full quick start sample. There's no mention of how many spaces go in. Because what I'm thinking is that if we are coding in a YAML string block, technically the number of tabs or number of spaces per tab doesn't matter while you're within the string block. So like I could tab these in 4 spaces or 2 spaces or 3 spaces, and YAML will still parse it the same. But in YAML, generally they'll use tabs to indicate your level. The suggested syntax is for YAML to use 2 spaces, but YAML will follow whatever indentation system that the individual file uses. Indentation of 2 spaces works very well for SLS. I don't know what SLS is. That's probably the SALT project or something. But it kind of sounds like Yeah, there's no requirement in YAML to indent any concrete number of spaces. There's also no requirement to be consistent. So for example, this is valid YAML. Okay, good. So what this tells me then is that we could make this whole thing more readable, or not that thing, this whole thing more readable just by doing tab sizes of 4. So let me undo all my changes to the properties, to the style. So I'll re-add those properties, and we're going to convert this back into YAML. And there we go. Good. Now this is the same as before, basically, but the key difference is that we're doing tab levels of 4 spaces. So let's turn the GLSL coloring back on. I think I've got it. I think I've got the middle ground that I care about. This is maybe more of a stylistic thing. But I think what we could do is we could just do braces as just a regular scope. So in GLSL, just like in C, you can do scope blocks to scope the variables to a certain, the names of the variables to a certain scope. We could do YAML basically, but then we do the braces to make it a little bit more clear where things start and end visually. And then it would have the additional benefit that the stuff that you declare inside of your main would be no, that's not going to work. At least it won't work for doing things like modules, because the modules may need these values to be visible in the rest of the main function. So that's not gonna help. I don't know. I'm going to take a quick break. I'll be back in like 10 minutes. I'm going to be mulling over this question about which style to go with. And ultimately, we're just going to have to go with one and start working with it. We'll see how much we can get done today before I lose my mind. I'll be back in like 10 minutes or something. Alrighty, back. Confirm my levels are good. had bumped my microphone on accident. Now to move it back to being in the right position and range to hear me very well. Alright, where were we? So, yes, we were kind of coming up with the new format for shaders, and this is kind of like our version of Shader Lab, where we assemble the entire shader program from all the inputs, and all of the inputs can include other shader files. So when deciding what format to take, I think visually this was taking me a little bit too long to get used to. I have one last experiment that I want to run, and if it doesn't come out very well, then we will stick with YAML. I want to know whether or not this would look okay in plain JSON. So just a point of reference, because I don't remember everything about JSON from first glance. We're gonna have to do a little bit of setup. So for starters, you got the braces on the very outside of the file, and then we got the in quotes we have the key name, and then we have the colon, and then we have the value, which is also, well, in this case it's all quoted, but I guess it wouldn't have to be. Oh, hello! It's my favorite raider. Hey, TCap1. How's it going? How was your stream? I caught the first half, but not the last half. You know, it's great. I'm just going to use YAML. Yeah, I think YAML probably is okay enough for our purposes, and I'd rather just get this thing going. I streamed for like 1 hour with my Mac muted with, oh no! Oh man, that sucks. From an hour after I left, oh man. That's too bad, but I'm sure everybody was still interested in watching you code. Some people just have videos of people coding on in the background without any sound, just to have something on in the background. But did you get a lot done? Yeah, no, I think I'm okay with this. I think I'm okay with this style. What I've been doing is coming up with a whole new pipeline for constructing and using shaders and materials, and that's meant a lot of planning. Not very much coding happening today. For me, it was just a whole lot of thinking through this problem out loud. Not really. I went and do a sound music learning website. Oh, okay. Huh. Yeah, the do you think you're going to be doing your own art and sound and music for your game, or do you think you'll bring somebody in before you ship? You'll do it? Nice. Yeah, that's totally a valid award-winning strategy. There's all kinds of games that got really good with just a one-man shop doing everything. You know what I think I would really like for this? I think I would really like for the YAML formatting color on top, and then just make these specific blocks be their own color. I think this is the way that I'm going to do it. I'm just going to do a YAML file. The sections of source that are in GLSL will come in as strings, and then when we're ready to ship, at some point I'll do a extension for VS Code and VS and Xcode that'll do color formatting. That's YAML, like the YAML on everything except for these specific blocks, and then these will do GLSL formatting. Okay, yeah, I think that's fine. I think that's good. All right, let's commit to it and actually program the damn thing. Okay, so what I've been working through is how to do shaders in such a way that I can still have all my modular pieces, where I can do a system header sort of thing, where I can have a system add things to a whole bunch of shaders at once, so that I can just like have materials that use the Win system, and you don't have to do all the vertex math yourself inside of your material shaders just to use the Win system. And there was some complications arising specifically from how we would do batch textures, how other inputs and outputs would be defined, and I realized that I kind of had to look outside of GLSL to be able to make this work. So I'm doing something that's kind of similar to Shader Lab, but it's going to be in a YAML format, and it'll kind of look like this, where we've got name of the shader, dependencies. So this will be referencing shader modules, properties that are going to be used for materials. Maybe I should say map properties on this, because sometimes you'll probably want to render without actually using a full-on material. But properties for this shader if it's used as a material, and then you got these blocks that define your code. So you've got the vertex declarations, the vertex main function, the fragment main function. And then the point of this is that you define all of these inside of your modules that you include for dependencies, and those will stitch into the main function and the declaration section as well. So it's a little hard to visualize, but it'll stitch together, I think, fairly well. So I will save that, close. I will discard that, and we'll finally start to program this stuff. Okay. So associate texture to sampler, that's going to be a future call. So for now, we've got the simple test material state, which right now doesn't really do anything except for init a few things. Actually, it doesn't do anything at all yet. We've got a blank slate for which to practice this rendering code. So I guess the first thing to do would be to bind a material, or get a material reference. So we'll do using EP graphics, and this would be a material handle. This will be mat, and we'll say mat equals EP graphics. What do you? Oh, this is using, right? I meant to declare a. I switched modes in my head while I was writing the line. I want a EP material handle mat, and I will assign it EP graphics load material. We'll pass in a path. I think we were doing inside of the content / materials. So c/materials / simple material.epmat will be our extension type for enterprise materials. And then we'll need to do some stuff for updating and drawing. Let's start with just making sure that we can compile the thing. We'll implement load material first, and then we will go from there, because that's going to be a complicated enough step. I'm going to go ahead and add a cleanup call to this state. And in it, we will do EP graphics delete. Do we have a delete or release material? Release material. And we'll release mat. Okay. And then on the header, we'll need to do the void cleanup override. Good. And then we go to load material. Yep, in here, please. All right, and then we had a whole bunch of code that we had started to write before we started switching to RabbitYAML. None of it applies anymore. None of it, because almost everything that we had coded in here is now handled by the texture loading function. So we'll just delete the whole thing and kind of start over. Oh, it's returning a material handle. That's right. All right, so for starters, we'll have to do some file system stuff. I've already got the file header in here. I will do EP. Wait, no, we're inside of the enterprise namespace right now. So I can just do file, load text file. We'll pass in the contents of, we'll get the contents out of the material file. So that would be path as a parameter. And then we need to pass in the address of an output buffer. So we'll do an std string out YAML, or string YAML buffer. And we'll pass in, wait, is it an address of, or is it, yeah, it's by reference right now. It's a to-do item for me to clean up that API. So we'll just pass in YAML buff. Good. And then we'll say if that loaded successfully, then we will do a thing. Actually, what I'll do is I'll say if it's not equal to success, then we will do an error code and then return. And pass out the path to the error message. Okay, good. And then we return 0 because 0 is a null handle. That's the paradigm we've been going with for texture and shader handles as well. We'll keep it up here. And then from here we will do the parsing. We'll need RapidYAML for this, which we've already got. So we'll do an r-YAML tree. And it will be, I think we construct it from, I've already forgotten how you use RapidYAML. Let's open up the place where we were doing it before, just textures.cpp. Tree, here we go. Yeah, so we do a declaration. At what point did we do? Oh, this is where we save the thing. So we're populating it from data. On that one, yeah, so we do a tree, we do an assignment from parse in place. That's right. So we've got the tree, we say r-YAML, parse in place, and then we need to convert the YAML buffer to be the correct type. So r-YAML, I think that was 2C substring, and we pass in the YAML buffer. And so what this does is that the parse in place takes the, oh, this needs to be a mutable substring, right? So what this does is that parse in place will take this as an input buffer, parse it, and any changes that it needs to make to the buffer in order to construct a tree out of it, it literally will just use this memory. And so the tree structure will use pointers to this buffer when it needs to get string values out. So that way we're not allocating more than once. We're not even allocating the buffer when we do this declaration, I don't think. It's when we go to do the load text file, it will allocate the buffer then, and then the allocation is done. And so we've got the tree, we need the tree node, so I think we need to, I'm gonna need to keep the textures .cpp open to follow along because I'm still pretty new to RapidYAML, so I'm gonna need to use it as a guide. So we do need to confirm that the tree node is a map. So you get that from tree root ref. So I can actually just copy this whole thing. Yep, and then change the error message a little bit. Graphics load material, root node of material asset of material file. It will pass in the path and say is not a map. and then the path will be path. Okay. And we'll use Alt-Shift-F to run Clang format and get the line breaks exactly right. Cool. And then instead of returning false, we return 0, which is a null handle. And at that point, the buffer is, when we return, the buffer is deallocated automatically, which is good. All right, and yeah, at that point, we just get the nodes for all the things that we care about, and we do the checks on their types. So I'll pull open the simple material.abmat on the right here. Basically, the three basic keys that we need are name, shader, and properties. Inside the properties section, we could have one or more keys. If we don't have anything, then this is legal. We can just have no value for the sequence, I believe. But yeah, so we'll say REML node ref, and we'll have 3 of them. The first will be name ref, or name node. The next will be shader node, and the next will be properties node. All right, cool. And equals. We need to get these from the tree, so it'll be tree, right? Yeah, we do tree, and then we do these 4 braces, right? So on this would be tree at name is the key. Then this would be tree at shader is the key. And then this would be properties. Okay, good. And then we need to confirm that these are all of the correct type. So this would be, we just need to confirm that it's a key val pair. So this would be, we do node.isKeyVal to check that. If, I'll do this down below. If name node.isKeyVal, if that is false, or let me think about this. I could do false or false or false or I could do true. And then, yeah, this is easier. So name node needs to be a key val, shader node needs to be a key val, and properties node needs to be a sequence. I think we just do, yeah, it.is sequence. So if any of these things are not true, then we'll say EP error graphics the material file passing in that path again is badly formed, and then the path is the parameter path. All right, cool. And then of course we return 0 because that's what you do when you got a problem. Right. Cool. And then at this point, we just kind of parse through the elements. You know what, though? I wonder if I don't have any properties. Let me try this out. If I got rid of all the properties, I wonder whether his sequence would return true. That's an interesting one. Let me see if there's an answer to this. Let me close all these open tabs. We'll say YAML empty sequence. Like maybe I have to do like the square braces by themselves or something. Okay, so yeah, that's how you do it. So if it's empty, then it could still be valid. It would just look like that. So far so good. And at this point we got the name, shader, and properties node. We just need to get the values out of it. And then we need to do some registration stuff. So let's start by getting the values we need out of it. And then I will figure out how I store these values for later use. So we'll say name is equal to tree. Actually, it'd be equal to name node dot val, and then that gives us a C substring type, which is from the C4 library. And for that, we would do dot to stir. No, I think we have a helper inside of RapidYAML itself. So RYAML to cars. I think that's probably it. Let's look at the overloads. 2 cars returns a size T. It does accept a string by reference on the right, so I can do like this. And then pass in the reference to name. Okay. Right, and then we'll do the same thing for shader path. What are you complaining about? Argument types are no instance of overloaded function matches the argument list. Sure it does. Because it was saying that taking a look at that overload list again, we can take the mutable substring and then hang on. Okay, so this is a C substring, not a regular mutable substring. Does it have to be mutable? That'd be annoying if it had to be. How did we do this in textures? Okay, I guess I can just do dot string and it'll give you a C substring type. Right? Hang on. Restricted pointer to the first character of the substring. Okay, that's a little confusing. The one I like RapidYAML for a lot so far, but the one thing that drives me a little bit nuts is that I have to learn the C4 library a little bit in order to be able to use its types. Fortunately, the C4 library is designed to be really low overhead for things like embedded applications. So it's not like I'm losing performance. It's just I'm having to learn 2 things at once, and that's not fun. So in this case, what we can do is we can construct directly from the value. So this would be name node dot val dot stir, and this will give us a const car pointer. Actually, hang on a moment. It is just a const car pointer. Okay, so we don't have to do that thing. We don't have to use a getter. And then we pass in the length, which would be name node dot val dot len. Okay, and this will construct it in place. Perfect. And then we just do the same thing for shader path. And this will be shader node dot val and dot length. Okay. So let's think about how we want to use this information. When we go to load a material, we'll need to have a way to bind it. So that means that we need to know, I guess we just need to store everything that's encoded by a material file. We need to know which shader to load and bind. This will just be a path, basically. We would take and pass that into the existing load shader API. And then the name, I'm actually not 100% sure how I want to use the name. Probably this will just be something that we show in the inspector or the editor. Maybe inside of the console for, excuse me, for error messages. And then the rest of it is all the property data, which will be a little bit more. So I guess we'll need a map of sorts. So we'll need to map the handle to all these values. So we'll start with a basic map. This is a CPP file, so we'll do a static std map. We're in our CPP files, we have access to the precompile headers, so I don't need to include map. It's automatically included by CMake. And this will associate the type material handle with, I guess we'll want to have like a little structure associating the name, shader, and properties. So let's do that here. We'll do a struct. This will be material data, and then it will include an std string that's a name. It'll include an std string that's the shader path, and then we're going to need to have a bunch of types associated with paths for the properties. I'll hold off on that for the moment. Just for getting started, we'll be doing this piecewise. Name, shader path, and then in the map, this will associate the material handle to material data. And this will be mass data, I guess. Really original names. Okay. And then the map data, we need to populate it. So I guess we can do .inplace on this one. Well, it's a map, so what am I saying? So we would do map data at the return value, which actually now we got to come up with a return value. So now's the time to do that. So the way that I do handles in the system is that instead of having to pass around a object or pass around a pointer or something like that, I simply pass around an integer that represents the thing. That's literally just an unsigned int. If we take a look at the material handle, it's an unsigned int type. So the only rules for these handles is that they're unique and they aren't zero. Zero is, this is a nullable type, so 0 represents the lack of a material, which is why we return 0 on these. So I guess we just need to do a simple counting scheme. We could go crazy and like make like a pool of handles to make sure that we're always recycling the ones we discard. Actually, that's not too crazy, is it? I'm thinking my way through this. Realistically, when you're playing a game, you're going to be as you load scenes and unload scenes and load states and unload states, you're going to be creating and destroying a bunch of materials by loading them to and from file. So I guess it makes sense to have like a recycling scheme right up front to make sure that the handles are all properly recycled and we're never having any collisions. So what I'll do is I'll do a simple std vector, I guess. Realistically, this will never grow large enough to reallocate, but if it does, then it'll prevent a crash. So we'll do a vector of material handles. And this will be static. And it will be handles to recycle. Easy peasy. Except for material handle is the name of the type, not material handles. And then we'll need to have a size T. This will be the next next handle to assign. And it'll start out as 1 because it's going to be the first handle that we assign. So the way that this will work is that as we need to generate a handle, we check to see whether there's any handles that need to be recycled. If there are, then we take the element at the back and remove it and recycle that last handle. Otherwise, we will use the number at next handle to assign. There is a downside to this, besides just having a allocation of recyclable handles, besides having a vector storing recyclable handles. The first downside to this kind of a system is that if a handle gets returned, then gets immediately reassigned, then the handle can possibly enter a bad state. So that is, if you continue to use a handle in your game code after you went to release it, it would then immediately be associated with a new handle, or with a different material. So that might be a thing, because we want to make this foolproof. If a developer is working on a game and they say load this material and then use it with this shader, and they're doing their own rendering code, and then they forget to stop using their material after they call delete, or they call delete on accident or something like that, and then another system creates a material with that same material ID, then they wouldn't get they wouldn't have a way to check whether there's a problem. They wouldn't get any error messages in the code. Probably all that would happen would be that suddenly they're rendering with the wrong material, and it might not be in a place where they can easily see that. So actually, this whole handles to recycle thing is probably not a good idea. Well, it would probably be okay if we were recycling like in a round robin fashion. So that way it's unlikely that the very next frame after you delete a handle that it would be replaced with a new one. Well, for now, what I'll do is I'm just going to count up from 0 and continually increase the handles. And then if for some reason we wrap around to the maximum size T, which is a 64-bit value, and we'll probably never ever hit in most cases, then we'll have to do something to prevent us from attempting to reassign a stagnant handle. But yeah, I'll start with the simple, and we'll work our way up. So we got a static size T next handle to assign. Down here, we are going to say we've confirmed that all of the nodes that we need are present, and we can use another handle. So we'll say mat data at next handle to assign, and then we can do some assignment. So we can construct a element using name and shader path, like that. And then soon enough we'll be adding the other data for the properties inside of the structure, and then we say next handle to assign ++. So that way the next time we go to generate a material, it'll take the next element up from that number space, and we'll just never worry about we'll not worry about the possibility of a overflow quite yet, because first of all, it's super unlikely, and there's other things that we need to worry about. So I'll say a little note to myself to do handle integer overflow if there are crazy numbers of materials. And crazy, like in the astronomical sense. This will never ever be a problem. We're talking about a 64-bit number, which is like more than the number of particles in the entire universe, like to the power of itself. Big, huge number, fits inside of a size T. All right, and then for release material, we're going to go ahead and get the release code started. We're going to say if mat data dot count mat. So if we have an element inside of mat data, then we want to release it, and that's as simple as mat data dot erase. And I think I could probably call erase without raising an error. I'm not sure offhand, but that's not the reason that I'm interested in doing that if block. Dot erase, where's erase? Return value, none, iterator from the, exceptions, there's nothing, 3, 4. So except the first two doesn't throw any exceptions, doesn't do anything if the element doesn't exist, probably. Removes the element if one exists with keys equivalent to key. That's 3 and 4. Oh, because these take iterators. Okay, so an exception would be thrown. So I guess we do have to have that. But the main reason why I'm doing the check before I do the erase is because I want to have an error message if there's a problem. So if mat.count mat is false, then we'll say EP error. Graphics, release material, material ID, or material handle does not exist, and then pass out the handle. Cool, easy peasy. And eventually when we go to figure out the integer overflow solution, this is where we would do it. Okay, good. Oh, and then we need to return next handle to assign -1. Because we want it to be the thing that we assigned, and then we need to increment the count, so -1. Cool. So that's the loading process, sort of. For the sake of just validating that everything is working correctly, I'm going to print out this data when we get it. So EP trace, we'll do a trace log. It'll be graphics. I don't need to do a fully formatted message. We'll say name and shader, and simply write out name and shader. And this is just to confirm that everything is working as expected, parsing this file out. What are you complaining about? Shader is undefined. Oh, it's shader path. That's right. Perfect. All right. Let's confirm that at the very least we can load the YAML file and parse some of the data out. Okay. So for this, we'll go to the test material state, which is where we're doing it. And we do have the load call already, so let's hit F7, see if it breaks. Confirm that we didn't break something. It's not going to display anything quite yet, but we're going to at least confirm in the console that we are correctly reading the data from the material file. The annoying part about this architecture is that there's no way for me to shorten the number of files that I have to compile, because I have to compile it for a bunch of different targets with conditional compilation enabled to make sure that everything is working throughout the whole thing. All right, so there's nothing going on because right now the game state literally just doesn't do anything. But if we take a look at the load material call, it does say the material file is badly formed. Okay, we got a problem with the parser. What is that? Oh, the problem, hang on a minute. The problem is that this is supposed to be a sequence and I didn't make it one. So, yeah, it's a sequence of key value pairs. So main text is supposed to be a map associating the type and value, but it needs the little dash to indicate that it's part of a sequence. So that actually makes sense. We'll run it again now that I made that change. Debug console. All right, name, simple material, shader, and it's got the shader path. Perfect. So we're off to the right start. So now that we got the name and the shader, let's confirm that it can actually load the shader. So go back to the load material. Oh, sorry, not the load material. We'll go to the bind material call. And then in here, we will have to take the material handle, identify the shader path, and then use it. So we'll do const auto reference, and we'll use C++17 structured bindings to get the data out of the map. So the first element was the name, and the second element was... Oh wait, can we do structured bindings for actually getting outside of a data struct? I'd forgotten that this isn't a tuple, so I don't actually need structured bindings. So what I'll do is I'll do a const material data reference, and this will be data equals mat data at mat. And we will do, this is where I want to have W asserts. I think I mentioned this on your stream yesterday, TCAP, if you're still here. That I was planning for a while to do a special kind of assertion that just does warnings if there's a problem instead of doing full crashes. This would be a great place for me to do this. I would say W assert mat, and then if the material is 0, then we issue a warning and we move on instead of crashing. But as it is, I have to do this as an if statement. So if mat, and then issue a warning if there's a problem otherwise. You still here? Yeah, nice. Yeah, see, there's a number of people in the stream, but not a lot of talkative folks. How's everybody doing? I'll just have to manually type the error here. Graphics bind material. Oh, except for it's not if mat, it's if. So I will do a regular assertion on if mat. Hang on a second. EP assert mat, because you should never ever be calling this with a 0. Though that could probably still be a W assert, but whatever. Assert mat, and then this one will say mat's data.count mat. And here we'll say material handle does not exist. And pass out the handle in the error. Cool. All right, so here we go. So this is where we'll actually do the code. We've got the handle to the material data. So we'll need to get the texture loaded for starters. Let me think about this. Oh, you know what? We'll need to do this. We'll need to do the shader compilation step inside of the load material and then hold on to it. So inside of inside of material data, we'll need to actually have a texture texture handle. Wait, not texture handle. Shader handle. I'm trying to remember how we did that. People not chatting is quite common. Even some 40 viewer streams have no chat activity for like 30 minutes. Yeah. Yeah. Lots of lurkers. And that's totally fine. That's how I've that's like 99% of my Twitch viewing is not talking to people. So, oh right, okay. So I'm kind of remembering how this works. So in the graphic system, bind shader. Oh, but I have to include the shader header to actually use it. Shaders.h. If we do bind shader, come on, it accepts hash names, I believe, of the paths. So what's going on here? Material data, bind shader. Oh, it's thinking that I'm declaring it. Okay, that's stupid. What's up with you, IntelliSense? All right, so if we do a bind shader call, it takes the hash name of the shader. We don't do shader handles per se for shaders. We bind the name. And the purpose of this is that you don't have to have you don't have to pass the handle around everywhere. You can just have like one system at the very beginning during initialization of the system, load the shader and hold on a reference to it. And then elsewhere, you could independently load the shader, bind the shader using the shader name and not have to pass the handle around. Is something stopping you from making that W assert you want? I think I don't want to spend the time to do it. I'm on a roll with a thing that I'm in and I never get around to. It's like a refactor project. Not a huge one, but I would have to go in and make the change, and then I would want to, at that point, go through and find all the places that I wanted to use W assert before, and then implement them. So this is the equivalent of throwing laundry on the pile. I'm just gonna skip over it and deal with it later. Not a great attitude for sure, but it's what I'm doing because I want to do materials. I don't want to do assertions right now. Anyway, yeah, so inside of here, we need the shader to load. And the shader name, let me think about this. Yeah, actually, all we need is the shader hash name. So instead of storing the shader path here, I'm going to be replacing this with a hash name. And that's going to be the shader name. Hash names are just hashes, 64-bit hashes. And we have a system in Enterprise where we can compute those at compile time using Bob Jenkins' spooky hash algorithm, which is really fast, but not cryptographically safe. We just use it for the purpose of speed. And then when we go to do the assignment here, to assign shader path, before we do assignment of shader path, we need to actually do the loading of the shader. And actually I should do at this point, I can just do hash name conversion. But before we do the assignment, we actually do need to do the load. So at this point we would say load shader file, and then pass in the path to it, which is going to be shader path. And the way that shaders have worked up until now, and maybe going forward, let's think about this. The way that shaders have worked up until now is that the name of the shader program was defined inside of the shader itself. So if we look at simplematerial.glsl, this is where we had defined it. We had hashtag epshader, and then this would be the name that we pass into wherever we got. And the benefit here is that you don't have to associate the name of the file with the name of the shader. So that way you could just hard code like using a raw string, hard code the GLSL code that you want to pass to the compiler, and it would work, and you could still get the name out of it. I think we can still keep with that with the new style of shader. We would just get it out of this name. And as an additional perk, switching to YAML, we can now support things like spaces in the names, because those are still valid strings and we can still hash them without issue. So yeah, okay. In here then. So load shader file, we would just pass in the path again, and then whatever the name was. Oh, I need to get the name out of the shader. So that's a change to the API. Previously, we would just return bool. We would return true if everything compiled correctly, and that was it. Because the assumption was that if you are loading the shader, you know what name it contains internally. That's no longer the case. So it's possible then, because we're doing materials, we have to be able to parse out the name of the shader from the compilation. I'm not quite ready to start the compilation step yet. We'll get there, because that's gonna involve replacing my entire pre-processing step with basically a YAML loading step and then an assembly step. Stitching together a working shader as opposed to taking and decomposing it from GLSL. But for now, we're going to need to change the way a load shader file works. Let me check for all the places that I use it to make sure I'm not breaking anything if I change its API right now, because I still want to compile and confirm that this all loads correctly. It's used in materials. That's the file we're in now. It's used in shaders.cpp. No, it's not. This is the definition, so that's where we would change it. It's used inside of test state, which we're not using right now. But it will still compile, I think. So let's comment that out. And then look for bind shader. We can leave the bind shader call in there and it'll compile. And then renderer 2D, of course, uses it. I will now take this opportunity to finally remove this change from the file. Up until now, we've been kind of hacking together a renderer because we didn't have a material system. So I had these extra lines inserted that I haven't been committing, where it'll load a particular shader, bind it, and unload it. Now that we're switching to materials, we can finally start doing this for real. So I'm just going to get rid of the lines of code that would be using the API, and then we'll come back to this after materials are working. In either case, renderer 2D is offline while we're doing this work, so that should be fine. All right, cool. And now I've got latitude to change this API up. All right, so load shader file and compile shader source. These are separated for the sake of being able to compile a shader that compiling a shader without a source file. So you can just hard code it in your C++ or your C file. You can do a raw string that contains your shader source. We're going to keep up with that. However, the compile shader source will be accepting not the GLSL meta format that we've been using, but the this EP shader format, which is YAML. And then for a return value, we're going to need to get the name of the shader out of the compilation process, which means that compile shader source needs to return it somehow. We could either do it as an out parameter, so it'd be like a const car star out, or not const car, a regular car pointer out. No, it would be const. What am I saying? No, it would be not. It would be mutable, right? Where this would be assigning out to a car variable, and this would be like out name or something like that. However, we could do better than that. We could do a return value that is essentially nullable. So let me think about this. We could have it return an empty string, or we could do like an std optional and do an optional string. How weird would it be to do an std optional string? I think it's still pretty clear what we're doing here. Optional, of course, is the C++ way of doing nullable types. So std string is not technically nullable. It's possible to have empty contents, but making std optional makes it so that it's officially nullable, and you can confirm the presence of something separate from its value. Yeah, so I think that's probably, well, I'm having to think about ergonomics here for developers who are learning how to use my engine. Yeah, this is probably not super clear. I think what I'll do is I will do Boolean still, so Boolean to return true or false about whether the compilation process was successful. And then we will do, I'll do a address of an std string. So we'll do std string pointer, and this will be name out. And then on the side that you are doing the compile shader source on, if you care about getting the name out, then you would pass in a string, the address of a string object to populate. And so inside of the compiling code, we'll do a null check. We'll say if this is null, then we skip it, because realistically, in most cases, if you're calling compile shader source as a developer, you already know in advance what the name of the shader is. Otherwise, you can do you can pass in a buffer to receive. All right, and I'll quickly update my documentation here so that it'll reflect nicely in the HTML documentation that we generate later. This will be the address of a string to receive that will receive the name of the shader program. Yeah, okay, good. And then I'll need to go into, even though we're not at the point where we're going to be doing shader compiling yet, I do need to change the signature inside of here. This will take the std string pointer and it will be name. And then we'll just leave the whole GLSL preprocessor stuff, which is like 2,000 lines of code or something like that. We'll leave all of that as is for the moment. Okay. Is there a problem still? What are you complaining about? Load shader file. Oh, did I change the load shader file signature? No, I didn't. Too few arguments. Oh, right. So there's places in here where I call compile shader source that I gotta fix. I'm gonna say I gotta make that optional. Let me go back to the signature, and then this name out can be equal to null pointer by default. And then that way, all of this code will not be broken anymore. Good. And you get the picture that is nullable when you're looking at this. Okay, cool. Back to materials. Test state. I can close test state, can't I? Yeah, I'll save and close. All right. So now we're doing load shader file, passing in the path. I need to get that name though. So we'll do out of, and I need to do a little bit of rearranging. So we get the name out of the name node. We get the shader path out of it. I will take. Oh, hang on a minute. I just realized that we don't actually want to do a return value of a string. Because in all cases where you're going to be receiving and comparing it, you're just going to be comparing it. You're not going to be displaying the name anywhere. So that actually should be a hash name. But yeah, this will be shader name. So what we'll do then is we'll do... I didn't think about this. I need to head back to the header we were just in, shaders.h, because we're actually not going to need, we're not going to want the whole string. We're just going to want this to be a hash name. And hash names are nullable. That is, I've reserved 0 to be the absence of a hash name. So, yeah, so that'll simplify the API a little bit. And we'll say name out, and we'll say oh, because hang on, this is nullable. So what I can do then, I can make this even simpler. I can take the API back to where it was before, except change the return value to be a hash name. Okay, good. And then on the return value, this will be the hash name of the compiled shader program. And because that's nullable, you can still say if compile shader source, and so on, or you could take the return value and then assert on it. Okay, that makes sense. So let's fix what we just broke inside of shaders.cpp. Compile shader source. Okay, so when we do load shader file, we get a return val, which return val is a Boolean. Going to sleep, have a good stream. Thanks for coming in. Thanks for the raid. Take it easy. I'll probably catch you on your next stream. Yeah, so the difference here though is that the return val is going to be a hash name. And I'm gonna rename return val to be shader. We call it program name. Oh, come on, there's only 2 references. Are you actually confused? Okay. Cool. Right, and there's a little bit of trickery going on here. Compile shader source actually takes and references the path of the file that's loaded in error messages. So we actually have a static variable that tracks which path we are on, and so we set it to the path before we call, and we set it back to null when we're done. All right, cool. And then here we would say return hashname null, which hashname null is just a macro that's 0. Right? Hang on a moment. Yeah, hashname of 0. What? Why isn't that just 0? I was so sure that it was nullable. Hang on. Did I not do nullable hashes yet? Okay, so so that's actually a little less elegant. Let me go ahead and make this change. Hash name null 0. Just because I want to be able to use if on a hash name and use its return value as a condition. Yeah. So hash name null 0, and then when we go to do the actual hashing, we would be calling return hash 64. Good. We actually need to confirm that this is not 0. So rather than coming up with a rather than doing like a bizarre min-max scheme for this, because a 64-bit hash is so freaking large, it'll basically never ever collide with one particular ID. I will at this point just say EP assert slow on this value. So slow meaning that it'll only run in debug builds. And the way that we use hash names, we do collision checking during debug builds, but nowhere else. So we'll say unit. I wonder why we don't just do this. This is code I haven't touched in a very long time. Hash name return val equals this, like that, and then we assert that it's non-zero, and then we return it. Okay, and then we'll have to do the same thing for this, the offline version. We have a string literal operator for hash names for the sake of being able to use hashes in switch case statements, because these have to be evaluated at compile time, and technically speaking, with interning it's not, and we intern strings when we are not in release. But I do need to do the assertion inside of here as well. So hash name hash, and then we can say EP assert slow, so that way development builds are not affected. The only ones that are affected are the slowest of the debug builds. And we'll say assert the hash. Cool. Good. And then, actually, I'm just going to call this hash as well. It's a better name for it. Like that. Perfect. And just like that, we've got nullable hashes. I don't know why I didn't do this before, but I didn't, and now I've done it. Cool. And then back inside of the load shader file stuff, source, we check to see if it's loaded, and then we call compile source on it, and then we set the path back to null, which is now 0. Return the program name. Okay, so the return value of compile shader source we need to still handle. In this case, the program name is not being kept, but it does need to be returned. So actually we need to change this API as well. So load shader file also returns a hash name, and it will be the same kind of return value. So just paste the return documentation from above. So when you compile or you load the shader file, you get back the hash name, not the bool. Okay. Good, and then back in shaders.cpp, that should have broken a few things. Like that. Hash name, load shader file. Cool. And then we would return the program name, or we return hash name null. And then in here, the actual compile shader source call. We now have a different signature. Compile shader source takes in a string reference for the buffer and then returns out the hash name of it. So shader hash name equals hash name null. And then when we go to return, we have been, and this is just the crazy nested if statements that come with a GLSL preprocessor. We've been returning false whenever there's a problem. That code still is technically valid. However, we need to do better with the return true. So yeah, so in this block then, I'm going to collapse and then select the whole thing, and then Control F inside of that block for all of its instances. Oops, I screwed up. Where did it go? Compile shader source. Here we go. Compile shader source. I will collapse the whole block, select it again. Control F inside of that block, and we were going to search for every case of return 0, or sorry, return false. And every time we do that, we're just going to return hash name null. So we'll replace with return hash name underscore null, like that. Good. And then in any place that we would return true, we need to replace with the returning of the hash name. So let's take a look at the return true situations. Graphics compile shader source. Shader program was previously compiled from a different source location. Check the shader source files for name collisions. Right, this would be if you have multiple shader files and the EP shader line has the same name in both of them. And we get this by checking shader source paths for shader hash name is not equal to whatever. Yeah, so at this point we would be returning shader hash name. Okay, and that's probably going to be the case for the rest of these two. Shader program was previously compiled from a different source location. Yeah, this is just another situation where you another parsing scenario which means the same result. So we return the shader hash name in this case because they're identical, or they have the same name. Same thing here. Previously compiled from, yep, check for name collisions. That's good. And then this is the same thing. Shader program was previously compiled from a different source location. All right. Good. Now, where else do we return inside of this function? Okay, so down at the very bottom, we have a return all variants is successful, which is a Boolean declared where? At the very start. Okay, so all variants successful is the tracking bool to see whether or not we successfully compiled every variant inside of this file, because we had not gonna go into it right now, but you can branch off multiple versions of a shader from the same shader file. We're going to keep that Boolean, but the difference is that instead of returning it, we will simply say return shader hashname. Else return hashname null. Cool, and we can do this all in the same. Both of these are just one line, so I'm not gonna do a block for them. Cool. All right, and then that will. I think that's it. I think that's the entire thing. Let me confirm. So selecting the block again, and then we're searching for every use of the return keyword. Return null, 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 null. Return shader hashname, 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 null, null. And then, yeah, okay, perfect. So that's fixed. And then we return the return value of compile shader source in load shader file. Okay. It's occurring to me though that I haven't checked for use of compile shader source directly. Here we go. So there's only one case where we are using compile shader source directly. That's for EP null shader, and we already know what the shader name is, so we don't store the result. So yeah, we're all fine. All right, that was a lot of refactoring. And if you think that was fun, just wait until we replace the GLSL preprocessor. All right, and then back to materials then. So in materials, we loaded the shader file. We need to store the name. So now we can do hash name shader hn equals load shader file. So when we go to load the shader file that's specified by the material file, we then get the name of it out, and we can store it here inside of the mat data map. Okay, and then the mat data map now contains the name of the. Hang on. We don't need to store the name. No, we need to store the name of the material. We don't need to store the name of the shader. Okay. So for this, I'm going to change it to say mat name. And this will be shader name. Cool. Cool, cool, cool. And then, yeah. So at this point, when we're doing the bind material, we now have the data, which contains the name of the material and the name of the shader. And that's perfect for our purposes. At this point, we know the name of the shader to load, so when we go to bind it, we can do bind shader and pass in data.shader name. And that's it. This is all it takes to make sure that the shader is active. However, when we go to load the material, we do actually need to do, let me look at this. Oh no, we've got it. Load shader file will compile, it'll load the shader at this path into memory, compile and pre-process it, and then add a reference to it. However, what this means is that every time you go to load a material, that material will add a reference to the reference count of the shader that it uses, which means that we're going to need to release it at the cleanup stage of materials. So do we have a materials cleanup call? I don't think we do. Materials.h. Okay, so we're going to need to add a new file. Fun stuff. Inside of, close you out. Inside of the EP internal headers, we need to add a materials.h. So So include enterprise EP internal, graphics, new file, materials.h. And that means, of course, we need to add this to CMake. So inside of CMake lists, we'll look for protected headers. Gonna quickly scooch over these into the here so it's easier to follow. And we're looking for the graphics, engine protected headers, time, events, file, graphics. And then graphics underneath textures, we'll do the internal header for materials. Actually, that goes below fonts as well. So it goes textures, fonts, because fonts are technically textures, and then materials. Cool. Control S to make sure that it builds correctly. It should. Build files written. Perfect. And now inside of the materials.h, we can include the public materials.h, which is in. Actually, this is a header, so I've got to use square braces or angle braces. This would be enterprise graphics materials.h. Perfect. And then we can do declarations that are private here. So we're going to do void or namespace EP graphics, and then do void init materials, and then void clean up materials. Though now that I'm thinking about it, we don't actually have any setup that we need to worry about right this moment. So we'll just do clean up materials. Save that, close that. Yep. And then in materials.cpp, we're changing the include for the main file. We're changing that to be the internal version, like that. And realized I need to do a little bit of reordering. Core file graphics, perfect. To get our correct header include style, which is the main library stuff and then project stuff. Cool. And then at the bottom of this, we can now do void clean up materials. And then from here we do what we need to do to unload the references to the shaders. So we would go for const auto reference with std structured bindings, associating the handle of each material that's loaded with its data. So we'll get the handle and the data for every material saved in the map, which is mat data, I believe it was. Right. And the handle is material handle, and then the data is material data. Perfect. So in this case, we're just iterating through all of the loaded materials, and we're just calling release shader. Wait, delete shader? Delete shader. And we have to pass in the hash name of the shader that was loaded. So this is going to be data.shader name. Cool. And that decrements the count for the reference count for all of the shaders that have been loaded. Perfect. And we don't even care about the handle in this case. However, this is the cleanup call, so we do need to clear mat data. Like that. All right. However, this brings us into the topic of reference counting, and it's a very important thing to do. And I'm already technically having to juggle reference counts with textures, so I should probably implement that now. When you go to load a material file, you pass in a path to the material. If multiple parts of your code or multiple systems reference the same material, we don't want to be compiling that shader a bunch of times. Or to be more correct, we don't want to be making instances of material data. Because the shaders are technically already reference counted, it's not like we would be compiling a bunch of shaders over and over again if we loaded multiple materials that use the same shader. However, we would be getting another element in Matt's data, which means that each instance of the material that we load would have its own copy of the property data, which, again, we haven't implemented that yet, but we will, so we need to handle this. So we'll need to do, I'm going to add a element in here, size t, ref count. So inside of the material data, we will track how many times it's been loaded and utilize that going forward. So when we go to load material, what do we got going on here? Load material, we get the path. We're going to need to reference count. Let's reference count against the material's path, not its name. In fact, I'm going to go ahead and just get rid of the name of it, of the material. I don't think the name is. No, you know, let's keep the name. The name will be used inside of the editor, but we're not actually going to use it for anything practical. So in a shipping game, it's not going to be relevant. We might want to conditionally compile it. I don't know. I'm on the fence yet about how to do string interning for hash names. I'll come back to it. But we'll have a ref count here. What we'll do is we'll have to check. We'll say if ref count, or sorry, if mass data dot count ref count, or not ref count, dot path. We're associating. Oh, this is going to be a little tricky because I need to associate the reference count with the path, not with the handle. Okay, so this is actually going to be its own thing. We're so changeable. So instead of doing material data struct map, we're going to do a separate map that's just reference counts. So this will be std map associating the path. So this will be std string associating that with size t, and this will be the material ref counts, or just mat ref counts. And this will be what we checked for the path right away. So we'll say if mat ref counts dot count path, and we use the path as a key. Then we basically just increment its reference count and then return it. So we'll say mat ref counts plus plus, or at path plus plus, and then return. We need to return the material handle for it. So yeah, so we'll need to do we'll need to associate more data with the string than just how many there is. We also need to associate the handle to return. So what we'll do is we'll do another struct, because I anticipate we'll have to add more data to this in the future. The struct will be material reference, or ref count data. And inside of it, we will have the size t, which is going to be the count, and then the material handle. Simple enough. And then the ref count data will be populated with elements of material ref count data. Okay, and then this will be mat ref data. And then down here, if mat ref data dot count path, then we will increment its count member by 1. Right? What's wrong with you? Mat ref counts. Mat ref data. Okay. We'll increment its count, and then we will return its handle. Though to make this a little bit nicer to read, I'll do a auto ref. We'll do path count. I think is what it was. No, it's count and handle equals mat ref data at path, like that, and then we can just pass in. We'll just do this. Cool. All right, and then we'll have to do reference counting. Well, there's two things we'll have to do. We'll have to do the opposite of this when we go to release the material. And then down in the loading, when we actually get the handle down here, mat data, handle to assign, we'll actually need to populate the reference count as well. So that'll be mat ref data at next handle to assign equals, or not at next handle to assign, at path equals, I think it was count and then handle, and the handle is going to be next handle to assign. The count is 1 in this case. This is the place where we add narrowing conversion from unsigned long to unsigned int. How's that? This is a size t, and oh, count comes first. That's right. Okay. Wait. No, count comes first and then handle. Count then handle. So what's up with you? Static size t. Material ref count data is count and then handle. They're both size t, so what's the... Oh, because next handle to assign is a size t, and okay. So actually, next handle to assign, I need to change that. That's not going to be a size t. That's going to be a material handle, just to make sure that all the types are correct. Okay. Got it. Okay. So far, so good. But yeah, down in here, when we go to do the assignment of the handle, we pass in next handle to assign to the key of the mat data, and then we do a storage of a ref count of 1 and the handle to mat ref data, so we can do the reference counting thing at the top. All right, cool. And then in release material, we need to do reference counting as well. So let me think about this. So instead of just going straight to delete, first we're going to need to confirm mat data. All right, I think I've got this. So instead of counting mat data, we'll do mat ref data dot count mat. right? No, it'll be mat. No, the first way was correct. Mat data.count at mat. We then have to do the decrementing of the references. So we'll say oh, can you take apart a struct with structure bindings? It just occurred to me that I just did structure bindings on a plain struct type, and it seems to be working perfectly. That's interesting. Okay, I'll keep using it. So we'll do auto reference count and handle. Equals mat ref data at, and we'll need to do mat data. We'll need to access the members of mat data here. So mat data, okay, auto reference, and mat data has a bunch of things in it. So I guess we'll do a mutable material data reference. And we'll say data, and we'll assign that equal to mat data at mat, and then we can do data dot whatever. So we need to access the mat ref data, and we'll do that from data dot. Oh, that's tricky. I guess we're gonna need to store the path associated with the material, because we index into mat ref data during the reference counting stage of load using the path. I guess that's what we'll have to do. So inside of material data, then we've got the name, we've got the shader name. We'll also need, I'll do this like this, hash name path hn, or hash name path. So that we'll store the path to the material file hashed, and then we can use that to look up into mat ref data. So mat ref data is now going to take a hash name instead of an std string. Okay, and then down here we say count. We'll do the hash name of the path. Actually, better yet, we'll cache it because we have to use it later. Hash name path hn equals hash name of path, like that. And then we count path hn, and then in here we get the count and the handle. The structured binding no longer directly works, so I'll do is I'll do a mutable reference to material data, call it data, and this will be data.count, data.handle. And then the key is going to be path hn, which is now the hash of the path instead of just the string path itself. What's wrong with you? A reference type of EP graphics material data cannot be initialized with a value of type. Oh, ref count data. Kill it. Yeah. Yeah. Okay. Ref count data, and then it has got count and handle. That's not cleaner than what I had before. I just got turned around by what type this was supposed to be. So we'll go back to the structure bindings, but I need to pass in path hash name for this to resolve. All right, perfect. Good, good, good. And moving on. mat ref data at path 1, next handle to assign. This is now going to be the hash, which we cached up above, so we can do path hn. Perfect. And we're passing in the next handle to assign, a count of 1. And then the last thing to worry about is the mat data, because the mat data now accepts the path hash, so we need to provide it. Okay, mat data at next handle to assign, name, path hn, and then structure shader hn. So we're storing the 3 things we care about here. This is C++ 17, otherwise I would be doing the named aggregate initialization for the structure, but instead I have to do it in the right order, but that's okay. Name, path hash name, shader hash name. Cool. What's this used for? Not used for anything anymore, I don't think. Okay. Shader path. Shader known value. Okay, so we get the shader path, we pass it into load shader file, we take the return value, which is the shader hash name. Alright, cool. I think I'm following. Okay, if matdata.count mat okay, so now we're back to where we were releasing the material. We check to see whether there's an element of mat data with the mat handle in it. If there is, then we get that data and then we use it to get the path hash name, and that allows us to pull out the count and the handle for it. Do we care about anything else in data? Path shader name. We do, actually. So I'll do a structured binding thing for material data as well. Mat name, we'll copy these. So the first would be auto ref mat name, path shader name. Except for instead of calling it path, it'll be mat path. And then shader name, it's going to be from the program. Okay. And then this will be getting the count and handle from mat ref data from mat path. That said, though, we need to have a assertion here. Because we are asserting that mat ref data and mat ref data and mat data have parity, that there's one element for each key in the other map. So we need to confirm that mat ref data.count has the same element associated with it, but using the key of mat path, if that made any sense out loud. And we'll use slow because this is probably going to be a hot code path, and we only care about this in debug. Okay, Good. Now we've got all of our things. Okay. And then count and handle. We're going to rename this to be mat count and mat handle. So that's everything we need. So mat count minus minus if mat count, which what is mat count? The size t is equal to 0. I'm going to say less. Well, it can't be less than or equal to 0 because it's unsigned. So if it equals 0, if we've hit 0, then we need to do the unloading. And this is where we would do release shader, actually it'd be delete shader. I'm going to give that a different name when we get to that, redefining that function. Delete shader, and we'll pass in the shader name. And then that'll decrement its count. And if it hits 0, then the delete shader call will handle the deletion of the actual shader program object, as well as the tracking for it, which is good. And then what else do we need? So we decrement the reference count. If we hit 0, then we delete the shader. And then I guess we would clear out the arrays. However, the reference to mat count would break. So I don't know whether that'll cause a compilation failure, but if it doesn't, then we just have to be careful. We'll say mat ref data dot erase, and the key is going to be the mat path, and then mat data dot erase, and its key is going to be mat, which is the parameter we passed in up here. All right. I really didn't need to do all these structured bindings. Okay. I'll do a little cleanup here. So we'll say assert that it has an element with a key of mat data at mat dot path, like that. And then mat data at mat dot path, and ref data, we can get the mat count out of it, and we are not even using the handle. So I would take and pass this into mat count dot count. But that's kind of hard to read as well. All right, so this is how it worked with structured bindings. What we'll do is, instead of structured bindings, we will go back to the material data reference, and then data.path, and then this will be material ref count data reference, ref data equals mat ref data at data.path, and then we can just do data.count or ref data.count and ref data.count, and then this will be data.shader name, and then mat path is data.path, and mat is the same as before. And mat data at whatever dot path, that's just going to be data dot path. Okay, a little cleaner and easier to understand. Cool. And that's it, really. I am a little concerned about about the self-referencing stuff. Let me think this through, because the reference to these things is going to be passed in. Oh no, that's fine. We pass this into the erase call. We're not iterating through anything. Right, so this gets passed in, the element gets erased using the key at data.path, and then we go straight to deleting data, which is done by calling mat data erase using mat, which is the parameter. Okay, perfect. So that's the cleanup call. That's totally fine. In cleanup materials, we're going to need to call release material. So instead of looping through and calling cleanup materials, or sorry, calling a delete shader on everything, we're going to need to iterate through and call release material on all the materials. So release material takes the material handle. The material handles are inside of the they're the keys to the material data structure. So we'll say for for every material data reference, data in mat data, we've got data.mat name, path, and so on. What's wrong with you? Oh, this is a structured binding situation. So it'd be a auto reference, the key value pairs. The key is going to be the material handle. I'll just call it mat. So we got the material handle for the key and so on. So we have to call delete or release on every material inside of this. Oh, but that gets tricky because while we're iterating through mat data, calling release, let me think about this. Calling release on the key will cause that element to get removed from mat data. And while it's true that the element won't get released until the last instance of the same key, is map sorted? I think it is. Because if it's sorted, then this will be a non-issue. It's a sorted associative container. So it is sorted. That means that we'll have all of the... Let me think about this. We would have all of the same key in the same row. So it would go material 1, material 1, material 1, material 2, material 2, material 2, which means that, strictly speaking, the release will only be invoked on the delete will only be invoked on the material after we've removed it completely from the mat data array. But we're still talking about invalidated iterators. So what we'll have to do is we'll have to make a copy. There's not a lot of ways around that. So we'll do a static, a locally scoped copy of mat data. So we'll do auto mat data copy equals mat data. And then we have to iterate through it. And so for it, we don't even care about the data. We just go through and say release bind material, release material, passing in the handle that we got from the key of this. And so this means that every okay, this is fine. And then we can do EP assert. We're going to do an assertion that the mat data copy and the mat ref, the mat data and the mat ref maps are empty. Because at this point we should have gone through every material that was loaded and decremented all the reference counts, and then that should bring all of them back to 0, and they should be totally empty. If they're not, that means that we've got some screwed up code in here. So EP assert map data dot empty. We'll do EP assert mat data or mat ref data dot empty. Okay. Yeah. So we don't need to call clear on these, do we? No, we don't, because we're erasing every element. Okay, I think that's good. Reference counting is not hard in principle, but there's a lot of little things to track down. Make sure you got all the references incremented and decremented at the right times. And yeah, that's it. So cleanup materials will automatically clear out and release all the materials. Release material will take and decrement the reference count for it, for a material, and then I need to do an EP assert slow on mat to make sure that we're not passing in a bum material handle. When we do the load material, we check to see whether it's already loaded. If it is, then we increment the count and return the handle. Otherwise, we go through all this stuff. All right, cool. So that's reference counting. Bind. So that's reference counting, and we've got compilation happening. So let's confirm that this works. I'm going to throw in some comments to track what happens. I'll say EP trace incremented a reference count, and then otherwise we go through these steps again to actually load up the data. I'll put a little message in here to let us know that it worked. EP trace loaded a texture or a material from file, like that. And then release material, we will say EP trace decremented a reference count. And then if we go to delete, we'll say EP trace deleted a material, like that. Cool. Awesome. All right, and then the last thing to do before testing is that I need to invoke cleanup materials in the graphics cleanup call. So that's down here inside of the graphics.cbp. Basically, the runtime will call cleanup on all the systems at the correct times. After we do the font cleanup, we do the cleanup on materials. And to make that work, we need to include EP internal graphics materials.h. Cool. And that should be it. Right, IntelliSense? Right? Right? IntelliSense doesn't seem to think that we've got the declaration. Ah, underscore. I need the underscore. Good. All right, F7. All right, compilation error. What have we got? All right, failed. In file included error use of undeclared identifier. Oh, hashnames.h. I have an assertion inside of the macro now. I tell you what, I'm gonna not do the null check inside of the operator hashname. The purpose of this operator is so that way when you're doing like a switch statement, you can use it in a compile time situation unconditionally. So this doesn't return the string. It simply hashes it and returns the hash, and this is a compile time algorithm. So when you go to use it, even on debug builds, it will compile correctly as a switch case, switch statement. Whereas the offline version, we actually do string turning and collision checks. I think that's when we do collision checks on the runtime version, that's where we'll do the check for null. So I think that's good. I think that's a good compromise. Oh, that's an equal sign in my return. Whoops. Try this again. Unfortunately, the hashname header is used in a whole bunch of translation units, so we gotta compile all those. Yeah, this is taking an annoyingly long time, but no compilation errors yet. What was exactly changed in here? Oh, what I changed was making it return the hash name instead of returning the UN64T. Still don't know why that wasn't a hash name to begin with, but whatever. There we go. It compiled and we don't have any errors. Let's press F5, run it, and then take a look at the debug console. Alright, graphics compile, shader source, shader compilation failed. Shader source does not begin with EP shader. Loaded a material from file. That's interesting. So we failed to compile, and we loaded a material. So got some issues there, probably. And then I went to close it. It says, decremented a reference count, deleted a material. Okay. Hash name 0 does not have a intern string. Huh. There's a fair bit of confusion happening in my head. Hey, Olin, welcome. Did you watch the possibilities of creating cryptocurrencies token? Watch the YouTube cryptocurrencies token? Oh. I watched a YouTube video about it. It was fascinating and inexpensive. Every time Solana API is used, they charge like 100 times less than 1 cent. Oh, geez. Yeah, I could not care less about cryptocurrency. I know it's like the future of the human race or something, but it's like, for me, there's like the cryptocurrency doesn't actually solve any problems because we're already doing electronic banking all the time. No, I haven't. That's funny. They charge like 100 times less than a cent. The idea of somebody making like billions of dollars off of like 0.0001 cents per cent or something, like that's like, it's crazy, and it's crazy to me that that's how things work. How the people who at Visa and MasterCard, they like make huge amounts of money just because, like, what alternatives do you have besides Visa or MasterCard? Anyway, so welcome in. We are doing material stuff now. We're changing up how materials are loaded, how shaders that work with materials are compiled, and we're starting with the basics and working our way up. We started this stream with like a solid 2.5 to 3 hours of design work, designing how these systems will work. And so now we're implementing it. Right now, it looks like we've got some issues with reference counting and compilation failure checking on materials. So for starters, let's take a look at the... I've got a whole lot of windows open. Let's take a look at the material file that we're loading. That would be this one, cmaterial simpleshader.ep shader. Simplematerial.ep shader is loading up a... this is what a shader file is going to look like when we're done, but it's actually an invalid shader file, which is fine. That we need to check that a failure to compile results in a correct response inside of the engine. In our case, it didn't. If I go to, I don't think I have it open anymore. Let's go to materials.cpp. Materials.cpp, I said. Here. When we loaded the material, there was a failure to compile the shader. So let's find that spot and take a look at it. That was here. Shader hash name equals load shader file. Oh, so we get the shader hash name and then I don't check it for null. So I need to do if shader hash name is non-zero or is 0. I suppose I should probably do this as equals hash name null. Then we've got a failure to compile. So at this point we should return 0 to indicate that the material failed to load as well. Okay, and then we would say EP error, graphics, load material, shader, and then we can pass in the path to the shader. Shader failed to compile. And that would be shader path, which we actually have as a string, so I don't have to unhash it. Failed to compile, and it would be shader path is the parameter. So shader path failed to compile. And then I should say material will not be loaded. Cool. And then we return 0. So that should resolve that one error that we saw. So shader compilation failed. Shader source does not begin with EP shader. That's the old GLSL preprocessor failing to read my YAML. And then we got loaded a material from file. That loaded a material from file business should disappear, as should the decrement and the deletion, because we didn't increase the reference count, right? Because we don't even add anything to the data maps until we're done with this. Cool. All right, I think that's good. I think that's correct. So maybe the name should be parsed out later on, because we don't even use the name until down here. Good, okay. And then there was something else that caught my eye, that bothered me. Hashname 0 does not have an intern string. So there's, now that we've switched to 0 being the null string, we probably have to clarify a implementation detail of hash names. So this is where we hash. I'm going to search for that error message we saw. Does not have an intern string. So this is when we call hashname toString. We pass in a hash name, and then we check to see whether the intern strings has the hash name in it. I'm gonna set that breakpoint there and see where we're trying to call hash name to string on a null value. I guess it's during termination. It must be, because I don't see the message yet. I'll click close. All right, there it is. Release material, EP assert slow, mat. Oh, this is not the breakpoint I set. This is just an assertion failure. Okay, so how did this happen? Let's go up to the up one stack frame. So during the test material state, we call release material on that material reference. Oh, but the material reference is null because it failed to load. Okay, so this should not be an assertion then. Let me stop execution and take a look at that. In the case that we have a invalid material handle, we'll just need to do a warning and then continue executing. If mat is 0, then we'll say EP error, or EP warn, I'll say, because it's not, we're not going to enter an error condition when this happens, but it indicates that we try to delete a material that we didn't actually, hang on a minute. It indicates that we tried to delete a null material handle. All right, so we'll say graphics release material attempted to release a null material handle. And then we say return. Cool. And that way we just early out if the material handle is invalid, providing the correct message for it. But because this is such a, I'm going to do an if-def on this guy, and we'll say if-def EP config debug, and then grab it. I'm going to make this a debug only check, because realistically we're not going to encounter this problem at all during development. Actually, I'll do one better. I'll do if indef epconfig release. Because if you're working in development, you might accidentally release a material that doesn't exist. This check doesn't need to exist down here. This is basically just to give you a warning, because if you have an invalid material handle in the release build, it'll still be handled correctly. Like, we're not going to enter an error state because you tried to delete a null handle, but it'll give us a better error message in non-release builds. Yeah. Okay, save that, F5, and we'll go back to trying to debug that one thing we were trying to do. Okay. And then it happens when we quit. Let's quit. Oh, that's interesting, huh? Okay, so the best that I can guess is that previously you were trying to pass in mat, a 0 mat into the unhash algorithm. All right, that's a little bit weird. I can't explain why this code was being invoked. On a 0 value, but it's not doing it anymore. So I guess we'll move on and we'll cross that bridge if we get there. But yeah, now we've got better error messages for the failure to load. Shader compilation failed. Shader sources does not begin with EP shader, line 1. And yeah, okay. So now what we're going to test is confirming that a successfully loaded shader causes no trouble. So we're going to go into the material file we're working with. This is currently referencing the EP shader file. I'm going to give it the GLSL file instead. So let's give it the simple, we'll go to C shaders simple msdf.glsl, just because we have it handy. And we're not going to actually utilize the shader, but it should successfully compile. And so we should be seeing error messages in here. Okay, loaded a material from a file. Cool. And then if we go to close, it says decremented a reference count and deleted a material. Cool. Now I just want to quickly confirm that the shader program is loading correctly. So I'll go to shaders.cpp and set a breakpoint to watch for this stuff, or I'll just I'll put some console logging to find the problem. So vlog, what am I saying? We're going into compile shader source. Actually, we can do this inside of load shader file. Let's do that. So I'll set a breakpoint here, and I'll step through this, checking each path each time, and I should come across a path that matches the simple MSDF. So let's run this real quick. All right, so first, yeah, C shaders simple MSDF.glsl. And, oh, right, because we've unloaded the test game. This is the only shader that's being compiled besides the null shader, and the null shader doesn't go through this call. And we just step over file, load text file, and we got the buffer. And the buffer appears to have the GLSL source in it. That's good. And I'm not going to go through the compile process, but I'm going to step over it and looking at the program name, that's weird. We have a program name, but it's some really high number. Oh, program name, right. So this is returning the hash of the name that was compiled. So just to confirm that that's valid, and it's actually introspected it from the program, I'm going to try hash name to string, paste in that hash and hit enter, and it says simple MSDF. Perfect, and that's the name of the shader. So it looks like the shader compilation step is working fine in our material system. And then say continue, and the debug console still looks correct. Loaded material from file and close it, and then it decrements the reference count and deletes the material. And of course, when we delete the material, we call it delete shader. Let me actually test delete shader. Closing, the breakpoint hits, the program is the same hash value as before. Stepping over, shader ref count for a program. There's a ref count for the null shader, and there's a ref count for the non-null shader. And cool. And we call delete program without issue. Perfect. So that's a good amount of stuff done. We've been at this for 5 hours and 14 minutes now. I think I'm probably going to need to call it a stream and work on the rest of it, particularly the GLSL compilation stuff, later. However, before I'm done with this section, because we were just spending all this time doing the proper reference counting, I'm going to need to track. I'm going to need to do reference counting for the editor's play in editor feature specifically. So this should compile if I go to the editor and launch it through the editor. So the editor, you know, it's the editor, it's the same. We got the project loaded the same as before. However, the scene's not going to render things. If we go to load up the scene file, we got the sprites, the sprite entities. You'll notice that the sprite components are gone, and we can see nothing inside of the scene view. And that's because if we go to the debug console, we have a bunch of errors that say sprite is not a valid component type because, of course, we aren't using renderer 2D anymore, and it hasn't registered the sprite component type with the editor, so it doesn't know what they are. So it just skips over those, and it reads the transforms of the entities, and that's it. So we have the transforms, all the entities are in the right position, they have the right name, but we can't see them. However, play in editor will be intact still. Test game.cpp. So what we can do, I'm gonna stop playback and do this. We're gonna need to test that in GameInit. When we do start and stop on gameplay, that the reference counts for things that are, for materials that are added during gameplay, that those all get cleared up. So first, to get that going, we're going to say call regular game init when you're using editor play init. So when we go to play the game, it'll push the material state, or push the test materials state the same way that we were doing before. And then we'll just use the stop button to stop playback instead of having to implement the control. Wait, maybe it's already in there. Did I haven't added any controls yet. I'll worry about that later. And then when we go into, where is it? Materials.cpp. We're going to need to track the ref count, mat ref data for materials that are loaded and bound during editor play. So we'll have another map here, and we'll say if def EP editor will have another STD map, identical to matref data, but it'll be for the stuff loaded during editor play. Matref data editor play, like that. And then we'll need to go into all the locations where we were doing editing of matref data, and we'll need to optionally do the same changes to the editor matref data. We'll say if def EP editor. We'll need to do some decrementing. So I'll put this down here. So when we called count plus plus, I would say I would need to insert the key at path hash name. So we'll do path hash name, and then call count plus plus. Okay, I think that's good. And then we'll have a reference count increase during editor play. There's an additional condition though that I need to apply besides just calling if def EP editor. I need to have access to the runtime. Let's add that here. Enterprise application.h, right? Is that right? No, that's not right. It would be application run, EP internal /runtime. Application/runtime.h, that's the one. This gives us access to the runtime where we can check whether we're running and whether we're in editor play. I can't quite remember how this handles in here. So if application is not launcher and application runtime is running, that's the check we have to make. Right. And this condition here is to make sure that, first of all, that play in editor is active. And then if we're in the launcher, then that means that we're not in the editor. Technically speaking, EP editor is just to confirm that you're in a build that's dynamic. So EP editor and that we're not launcher. But that is accessed in application.h. What else is in application.h? Command line stuff. Part of me is wondering whether I should merge application and runtime again, but I'm going to leave them as they are for the moment. Okay. Cool. So when we go to load a material, we'll increase the ref count conditionally here. Otherwise, when we go to actually insert the element into matref data, we'll need to do the same for the mirror. Okay. Right. And so this would be matref data underscore editor play at path hash name equals the same stuff. But I'm actually going to do it like this. So that way if I make a change to this, it'll affect both. Perfect. And yeah. Oh no, that's right. That's right. Because if we're at this block of code, we're creating the first instance of the thing, so ref count would be 1. That's good. All right, and then the last place where we need to worry about is during release. Here we've got we do a decrement of the ref data.count, and then we unload it if it's equal to 0. We're going to need to do a decrement of the ref count in the editor, and then basically just issue a warning when it hits 0. Because the reason why we're tracking all these creations and destructions, or sorry, load and release of the materials, is so that way a game developer doesn't accidentally call release more times than they call load. So we'll do ifdef EP editor, and then here we will do the if we're not application is launcher, and runtime application is running. No, runtime is running. That's right. Then we will do the decrement. So that would be matref data editor play at data.path dot count minus. And if its count equals 0 at this point, then we've got a problem. We'll say EP error, and I'm going to copy the wording that we used in here. Attempted to delete texture that wasn't loaded during editor play. That actually should say release now. Attempted to release texture that wasn't, yeah. So I'll copy the wording a little bit, and we'll say graphics release material, attempted to release material that wasn't loaded during editor play. And then we'll say the material and pass the path out. That path being data.path, right? Or hang on a minute. Data.path is a hash name. So that'd be hn to string, so hash name to string, and we dehash the material path, and yeah, cool. All right. Yeah, that's looking good. All right, so to test that out, we're going to go to the materials. Huh. You know, we'll test it out later. I think we're fine, because this is a tried and true checker. However, when we get to hang on, how do we do cleanup after editor play? Oh, we need to implement editor play cleanup. Okay. Last thing, it's the last thing I'll do before calling it a day. Editor play cleanup is necessary to clean up things independent of the regular cleanup call. When you go to stop playback in editor, but you're not unloading the project. So we got cleanup materials. Cleanup materials, or editor play cleanup materials is what it's called. And that means inside of graphics.cpp, there's an editor play cleanup call here that we need to extend. We'll do, I think this is before uniform buffers actually. Or is it after? Materials, shaders, uniform buffers. Yeah, materials should actually be, yeah, materials should be cleaned up before shaders and uniform buffers. Right? No, it should be cleaned up before textures, actually. Let me think about this. I'm going to need to do some arranging on this. Materials, vertex arrays, materials, textures. So materials can load textures and shaders and uniform buffers. So it should be cleaned up before we clean up those things. Right. Good to catch yourself. All right, and then here during editor play cleanup, we need to do, yeah, we'll need to do materials after frame buffers, but before uniform buffers and shaders. Yeah, actually frame buffers will need to be up here as well. Okay, and then we just need to declare it inside of materials.h, like this. Good, and then, come on, what's wrong with you? Good. And then inside of materials.cpp, we've got the function call. We need to actually do the cleanup. So that's going to look like iterating through the material data. Where is it? The material ref data for editor play for auto ref thing and whatever. And I'll just double check what I'm looking at here. So this will give us the hash name of the material. Is that right? No, the hash name of the path to the material. And then the material ref count data. Yeah, so actually the call is going to look very similar to this. So it's going through every material. We're going through every material count. So what do we got in ref data? Yeah, we'll need to do this as structured bindings. Oops. And the key was path to the thing. So all right. So in ref data, we've got count and we've got handle. So basically, we'll need to at this point, at the end of editor play, we should have a 0 for every count. And if we don't, then we need to decrement the... oh, that's a little confusing. Let me think about this. So for every load that we've done, on a material during editor play, we need to have already released it. So if there's anything left in this, then path in ref data represents a release call that needs to happen. So I'll do EP warn, and we'll say editor play cleanup materials, and we'll say materials again. I'll copy the verbiage from someplace else where I've done a similar message. So we'll go to textures.cpp, take a look at what it does. Oh, it didn't actually give a warning. That's interesting. We just sort of cleared up. Okay, that's fun. So I'm gonna make myself a little note and say, in graphics.cpp, where we do editor play cleanup, I'm gonna say to do ensure that warnings are issued in the event of dangling handles. So that way you get a warning from the engine if you have failed to clean up after yourself. But I'll do the first one here. So editor play cleanup materials. Leftover, or I say materials are still loaded. Materials loaded during editor play are still loaded. Or I say we're not unloaded. Correctly. So materials loaded during editor play were not cleaned up correctly. And then this is where I say what the details are. We'll say the path or material, and so we got what do we got in there? We got ref data dot, oh, count is the other one. Hey Michael, how the fuck do you program without looking stuff up every 2 seconds? Oh, that's my secret cap. I'm always looking things up every 2 seconds. No, I totally look stuff up. It's just that I happen to not be needing it for. I don't need to be referencing a website for this. I need to be referencing my other code, and so I hop over to graphics.cpp to get information about how I did things over there, and yeah. Don't be fooled. I am totally looking stuff up every 2 seconds. Material, and then remaining count. And then from here we would say, what was it? Ref data dot handle, which is a. Oh, hang on. I'll have to translate the handle into a path. I'll come back to that in a minute. Gotta remember that one. Yeah. And then the references is going to be ref data account. Can I get? Let me look at this. Can I get the path from ref data? Oh, path is this. It's not in ref data. It's the key. And the key is going to be a hash, so we got to dehash it. All right. Hash name to string path. Perfect. So now we got a warning saying, okay, you forgot to clean up this material this number of times. That's really helpful. And then we need to clear out the reference, which is going to invalidate the iteration. So we got to do what we did up here, make a copy, auto mat ref data copy equals mat ref data for editor play. And then we iterate through it, and then we can say mat ref data underscore editor play dot erase, and pass in the key, which is going to be path. Bam. By the way, remember that I told you that I tried Valorant's API? Didn't work out, so now I'm trying to use League of Legends API. Oh, nice. I mean, they use separate APIs, so they don't even affect the same games, right? Like, it's not like you have like a Riot Games. Wait, hang on a minute. Is Riot doing both Valorant and League of Legends? Are those the same universe? I don't really know anything about League of Legends except for I watched Arcane and that was really good. Yeah, it's Riot Games. So is that part of? Okay, so it's not part of League of Legends. It's just by the same company. Okay. Believe it or not, that actually makes me a lot more interested in it. But I don't know, because everybody I know says fuck League of Legends. They can't handle the game and the player base. But I was really happy with with Riot Games world building in the show, and they do all kinds of cool things with like we're listening to their sessions playlists right now because they give a whole bunch of creator safe music to listen to for free. League of Legends is toxic as fuck. Yeah, probably. But yeah, maybe I'll try out Valorant now. I mean, like it was always kind of a back burner item before, but realizing that it's Riot Games, maybe it's that's a selling point, but we'll see. Anyway, back to where we were. So we have now checked every reference added during editor play. We now have to release it. So we're gonna say release material, and we need to pass the material handle, and that's going to be from ref data dot handle. And this will actually release the material or release the count that was added during editor play. So that way we're back to square 0 or square 1. So we'll still have the references that were created during the initialization of game systems, but we won't have the ones that were from gameplay code. Cool. Release, and then we have to release the data from here. The mat ref data from the actual reference counting, that's handled independently. Okay, and at this point, mat ref data editor play should be empty because we've iterated through everything in it and called erase on every element in it. So I think that's it. I think we're set. One last thing I gotta double check because I had forgotten about this, but remembered as soon as we had to do this editor play cleanup. I need to not release if we get below 0. Hang on a moment. Release material. If we're doing plain editor, we decrement the reference count here. If it hits 0, then we need to not unload it. So we'll change the order here. I chose League of Legends because you can access it through the same library called Riot Watcher. Oh, okay. What happened with Valorant? What happened when you tried to use the API for Valorant? What didn't work? Only companies are allowed to access Valorant's API. Oh, okay, I see. But the League of Legends one is public. Oh, you mean, oh, so third-party companies can access it, but you have to, that's kind of stupid, isn't it? The whole point is to make it available for folks to make tools with, but they only let big companies do. That's really weird. Do they license it? Like, do they have big companies pay money so that they can do apps for their game? That seems a little strange, doesn't it? Yeah. Maybe it's in like beta or something, and they're worried about cheaters that could utilize the API. Oh, it's licensed. Oh, okay. Yeah, that's not cool. I don't know why they would do that, because it seems kind of, yeah, it seems like it defeats the purpose a little bit. Because like you're at, so the idea of a company saying, hey, I'll pay you money if I can make your game better. That seems a little strange. Like how many people are selling apps that that interface with another video game? I don't know. Maybe not a lot. Now the app's still got to be free. That's so you have to pay money and you have to. Well, you didn't say pay money. You said license. So I guess the license might still be free, but you have to sign a license agreement as a big company. I don't know. That seems a little janky to me. I don't know what's up with that. Anyway, let me figure out this reference counting still. If we're in the editor play, and we have called release on a material, we check to see whether the reference for that is already 0. Well, actually, hang on. We check to see whether the key exists. So let me reverse this ordering I've done. We check to see whether the key exists. If it doesn't exist, oh, I'm getting confused. So there's .count data path. That's when you're checking. Okay. Okay, so I was right the first time. You're only allowed to use it if there's a way for people to use your product for free. That's interesting. Yeah. It's still a strange move because like most of the people who care about making these kinds of tools are the people who play the games, right? Huh. Oh well. I'm sure they know what they're doing. They're a wildly successful game company after all. Okay. If material ref data. Okay. So we're at this point we're inserting the key if it didn't already exist. If it does equal 0, then that means that we've just inserted the key. If it's not equal to 0, then we can decrement the count. That said, if we've reached the count of 0, I'm actually going to delete the element. Okay, so this is actually looking okay. So so that the map doesn't contain a bunch of empty keys, we continuously will remove the keys when the count hits 0. Okay, that's looking good. All right, perfect. F7. And that'll be, as long as we don't have a compilation error, then we'll be done for today. Come on. All right, F5, confirm it runs without breaking. So inside of the test game project we have loaded, we don't have sprite components anymore, but we do have gameplay. So if I hit play, take a look at the take a look at the debugger. It says we loaded a material from file. Perfect. And if I click stop, Then let's take a look at what we got. Loaded a material from file, decremented reference count, deleted material. Perfect, that's working great. And then at the very end here it says materials loaded during editor play were not cleaned up correctly. But it says the remaining reference is 0, so I screwed up the cleanup call. Apparently currently there are only 2 big companies that use Valorant's API, Tracker Network and Valostats. Huh, interesting. And then we have material handle 1 does not exist. Okay, so we got some confusing questions here. Alright, so I thought we were good, but I guess we're not. So materials loaded during editor play were not cleaned up correctly. And then we call release material. Oh, so it's trying to release the material because it seems to think that the material has a reference, but it doesn't. And because it doesn't, it gives that. So we've only got the one issue. Materials loaded during editor play were not cleaned up correctly. Here. So this is getting called, even though count is 0. Why would that be? Material is simple material dot epmat. Oh, I think, hang on. Oh, when we go to load up the material. Oh, okay, I think I know what's going on. I'm gonna hit a breakpoint here real quick. And do the start and stop play. The ref count that we're getting from this is coming from ref data, not from mat ref data. Wait. Ref data is the reference data from editor play. There's actually a separate... No, that's right. Hang on a minute. That's totally right. This is the reference counts for stuff loaded during editor play. We have a count 0, handle 2. So the texture that we tried to load or the material that we tried to load still has a key inside of this index. So hang on a minute. In release material, I'm not removing the element correctly. So this is where we're supposed to do it. So oh, okay. So what I forgot to do was this. So if we decrement the count and it hits 0, then we need to call erase on the element. But if we try to erase and it's already 0, that's when we do this error message. Okay, but you know what? I can do better than this. I can do .count data.path like that to say if the node doesn't exist, then we don't need to delete. We just issue the error. And to make this even more straightforward, I'll reverse the if and else blocks. So if there's an element inside the map, then we do matref data editor play, and we do the count decrement. And then from there, we do the erasure if we hit 0. And then this whole thing will reduce to a no-op when... This will reduce to a no-op when we compile in a shipping game. All right. Thanks, Joel. I'll take it easy. Yeah, I'll remember. I think right now I've got my brain is on food. I'll get there, and I'm pretty much done anyway. But thanks for popping in. I'm going to... Yeah, I'm just going to run this real quick. This should be everything. When we go to start and stop play in editor, we should have successful creation and deletion of a material. So play in editor is running. It says we loaded a material from file. That's great. And we hit stop. Decremented a reference count, deleted a material. Perfect. So that's you know, important basics to get out of the way. Today was kind of we got a solid start on materials, but the really fun stuff, which is going to involve advanced shader compilation and parsing and things like that, that's going to come in our next session. I may stream tomorrow. I don't know. If I stream tomorrow, it'll probably be in the afternoon or the evening instead of in the morning. And we can get started on that part of it. But for now, just to cover what we did today, we came up with a solution for shader files that makes it pretty straightforward for you to make a shader or a shader module that can be conditionally compiled into everything that you need for a material system. The material system will obtain the sampler types that you need for your textures. It'll obtain the uniform buffer members that you need for your other properties, and it'll even take in when we get to this point, we'll be able to do things like say color for versus vec4. To be able to inform the editor of which widgets to use instead of just doing a regular field. We can have a color picker for colors and then like a regular vec4 field for just non-color based vec4s. And then we identified how we're going to manage assembling a full shader out of multiple modules. We also integrated this into our scheme for material files, and material files are actually going to be way simpler to handle. It's basically just the name, shader, the properties, and the properties are a sequence. And we got simple parsing of this going, so that way we can load up a material file, and it will compile whatever shader you've provided inside of the shader line. And so far we've got it running to compile the old style of GLSL file shaders. Cool, and then we got reference counting working correctly, so that way material handles will be created and destroyed correctly, whether or not you're doing it in editor play. When we come back, we will be implementing the details of this, so that the first detail being we need to use the new style of shader compilation, which means dumping and replacing the GLSL preprocessor stuff that I've got going on. And then once that's done, we'll be able to go from there to populate material files with data associated with the stuff in the map properties block. Cool. Thanks for popping in. I hope you have a great weekend. If I come back in tomorrow, it'll be in the afternoon or evening probably. I'll spend the morning doing other stuff. See you later.